We have seen the edge of everything. 93 billion light-years from end to end, a sphere of galaxies and light and ancient starfire stretching in every direction around us. 2 trillion galaxies mapped, light from 13.8 billion years ago captured and analyzed. The observable universe laid out like a cosmic inventory, catalogued, measured, understood, and then the measurements stop. Not because we ran out of telescopes or patience or funding, but because physics itself draws a line and says no further. Beyond that horizon, there is only silence. But here is the question no one can answer with certainty. What is that silence hiding? Some scientists will tell you it is more of the same. Infinite space, infinite galaxies, stretching on forever in every direction, forever beyond our reach. Others will tell you it is nothing, not empty space, but the absence of space itself, a boundary where reality simply ends and the rules that govern existence dissolve into something we do not have words for. And then there are those who will tell you it is neither. That beyond our bubble of visibility there are other bubbles, other universes with other laws, other dimensions we cannot perceive, other versions of physics playing out in realms we will never touch. The James Webb Space Telescope has let us see closer to the beginning than ever before, 13.4 billion years into the past. Galaxies that formed when the universe was practically an infant, and yet the deeper we look, the stranger the picture becomes. Because the data is not showing us a simple, well-behaved cosmos. It is showing us tensions, contradictions, hints that something fundamental about our model is incomplete. So what lies beyond the edge, and what does it mean that we may never ever know? Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The observable universe is 93 billion light-years wide. That number should feel wrong to you. It should feel impossible. The universe is 13.8 billion years old. Light has been traveling toward us for 13.8 billion years. So the farthest thing we should be able to see is 13.8 billion light-years away. The math is simple. The answer should be obvious. And yet the actual number is 46. 5 billion light-years in every direction. Double that, and you get 93 billion light-years across. Somewhere between the simple math and the real answer, something happened that most people never stop to think about. The universe cheated. Not in a way that breaks the rules, but in a way that bends them so thoroughly that the result looks like a mistake. It isn't. This is the story of the visible frontier, the boundary of everything we can ever see, everything we have ever seen, and everything we will ever be able to observe, no matter how long we wait or how powerful our telescopes become. It is the edge of perception itself, and it is not where you think it is. Let's start with what the observable universe actually is, because the name is more literal than it sounds. The observable universe is not the universe. It is the portion of the universe from which light has had enough time to reach Earth since the beginning. Picture yourself standing in the middle of an enormous dark field at night. You turn on a flashlight. The beam travels outward at the speed of light, illuminating everything it touches. But the field is so large that the light hasn't reached the far edges yet. The part of the field you can see, the part lit by your beam, that's your observable region. Everything beyond that is still there. It's just dark to you. The universe works the same way, except the flashlight is the Big Bang and the beam has been traveling for 13.8 billion years. Now here's where it gets strange. The observable universe is a sphere, not a disk, not a plane, a sphere, and you are sitting exactly at the center of it. So is everyone else. Your neighbor is at the center of their own observable universe. An alien on a planet orbiting a star in the Andromeda galaxy is at the center of theirs. A hypothetical observer floating in the void between galaxy clusters, completely alone in the dark, is at the center of theirs. This is not because any of you are special. It's because the observable universe is defined by the observer. It is the region of space from which light has had time to reach you. The boundary is set by how long light has been traveling and how fast it moves. Since light travels at the same speed in all directions, the result is a sphere with you at the center. Move 1 billion light years to the left and the sphere moves with you. You're always in the middle. Not because you're standing still, but because the definition of the edge is tied to where you are. The edge itself is called the particle horizon, though some scientists prefer the term cosmic horizon. It's not a wall, it's not a surface. You can't touch it, you can't see it, and if you somehow traveled toward it, you would never reach it. The horizon is an observational limit, not a physical one. It marks the boundary between the part of the universe we can observe and the part we cannot, and that boundary shifts depending on where and when you are. Think of it like the horizon on Earth. When you stand on a beach and look out at the ocean, you see a line where the water meets the sky. That line is not a real edge, it's just the farthest point you can see from where you're standing. Walk forward, and the horizon moves with you. The particle horizon works the same way, except instead of being limited by the curvature of the Earth, you're limited by the age of the universe and the speed of light. So why is the observable universe 93 billion light-years across if the universe is only 8 billion years old? This is where most explanations fall apart, where the math starts to feel like a magic trick. The answer has nothing to do with light moving faster than it should, or time behaving strangely. It has everything to do with space itself. Space expands, it always has. From the moment of the Big Bang, the fabric of the universe has been stretching, pulling galaxies apart, increasing the distance between any two points that aren't held together by gravity. And while that expansion was happening, light was traveling. A galaxy that emitted light 13 billion years ago was much closer to us when that light began its journey. Let's say it was 5 billion light-years away at the time. The light started moving toward us at the speed of light, but while the light was in transit, space kept expanding. The galaxy that emitted the light drifted farther away. The space between us and that galaxy stretched. By the time the light finally reached Earth 13 billion years later, the galaxy that sent it was no longer 5 billion light-years away. It was 30 billion light-years away, maybe more. The light still took 13 billion years to get here because it was traveling at the speed of light the whole time. But the distance between us and the source of that light grew while it was traveling. Run that process across the entire history of the universe, and the math starts to make sense. The farthest light we can see today was emitted by regions of space that were relatively close to us when the universe was young. Over the billions of years that light spent traveling, those regions moved farther and farther away due to the expansion of space. Today, those regions are roughly 5 billion light-years from Earth in every direction. The light took 8 billion years to arrive, but the source of the light is now vastly more distant than it was when the photons left. This is not a violation of the speed of light. Light still travels at exactly the same speed it always has. Space is just bigger now than it was when the journey started. If space had not expanded, the farthest visible regions would be exactly 8 billion light-years away. The diameter of the observable universe would be 6 billion light-years. Clean, simple, intuitive. But space did expand, and the current distance to the edge of the observable universe is 46.5 billion light-years. The diameter is 93 billion light-years. That's the actual size of the region we can observe, the actual span of the visible frontier. Light from anything farther than that has not had enough time to reach us yet, and because the universe is expanding faster every year, some of that light never will. There's a boundary inside the observable universe that deserves its own mention. It's called the surface of last scattering, and it's the oldest thing we can see. When the universe was about 380,000 years old, it was still a hot, dense fog of hydrogen plasma. Photons couldn't travel freely because they kept bouncing off charged particles. Then the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, photons could move without interference. The universe became transparent. The light from that moment, stretched by billions of years of expansion, is what we now detect as the cosmic microwave background. It's a faint glow of radiation coming from every direction in the sky, the afterglow of the moment the universe went from opaque to clear. The cosmic microwave background marks the edge of the observable universe in a practical sense. We cannot see anything older than 380,000 years after the Big Bang, because before that moment, the universe was a wall of glowing fog. No telescope, no matter how powerful, can see through it. It's like trying to see past the surface of the sun. The light just scatters. So the observable universe has two edges. One is the particle horizon, the theoretical limit set by the age of the universe and the speed of light. The other is the surface of last scattering, the practical limit set by the fact that the early universe was opaque. They're not the same thing, but they're close. The cosmic microwave background sits just inside the particle horizon, about 46 billion light-years away in present-day distance. It's the oldest light we can detect and the farthest back in time we can see. Beyond that boundary, the universe still exists. We just can't observe it. Not now, not ever. Let's talk about scale, because 93 billion light-years is a number so large that it doesn't mean anything to a human brain. You need comparisons. You need something to anchor it to. Start with the distance from Earth to the Sun, about 93 million miles. Light takes 8 minutes to cross that distance. Pluto, at its farthest, is about 40 times farther out. Light takes roughly 5.5 hours to get there. The nearest star beyond the Sun, Proxima Centauri, is about 24 light-years away. Light takes 24 years to make the trip. The Milky Way galaxy, our home, is about 100,000 light-years across. Light takes 100,000 years to travel from one side to the other. The Andromeda galaxy, our nearest large neighbor, is about 5 million light-years away. Light takes 5 million years to cross the gap. Now multiply that distance by 18,000 and you're roughly at the edge of the observable universe. 5 billion light-years. Every star, every galaxy, every cluster, every supercluster, every filament of matter threading through the cosmic web, all of it sits somewhere inside that sphere, and all of it is expanding away from us. The farthest galaxies we can currently observe are so distant that we see them as they existed more than 13 billion years ago, when the universe was less than 1 billion years old. They were small, dim, chaotic. By now, today, in the present moment, those galaxies are unrecognizably different. They've merged with other galaxies, formed trillions of new stars, and drifted so far away that the light showing us their current state won't reach Earth for tens of billions of years. We are not looking at the universe as it is, we are looking at the universe as it was. Every photon that hits a telescope on Earth is a fossil, a relic from a moment that ended billions of years ago. The farther out we look, the farther back in time we see. The edge of the observable universe is also the edge of observable time. There's something deeply unsettling about that. You are sitting in a bubble 93 billion light-years wide, surrounded by a horizon you can never cross, looking at light from objects that no longer exist in the form you're seeing them. And outside that bubble, the universe continues. Galaxies you will never see are forming, evolving, dying. Stars are igniting, planets are cooling, maybe life is starting, maybe civilizations are rising. Maybe someone out there is pointing a telescope in your direction and seeing the Milky Way as it existed billions of years ago, a younger, smaller version of itself. You will never know, they will never know. The observable universe for them is a different sphere, centered on them, containing a different set of galaxies. Your observable universe and theirs might overlap, or they might not. If they're far enough away, there is no overlap at all. You exist in completely separate visible regions of the same universe, forever isolated by distance and time. Here's the uncomfortable part. The observable universe is not static. It's growing, but not in the way you'd expect. Every second, light from slightly more distant regions enters the observable zone. The particle horizon expands. You'd think that means we'll eventually see everything, that given enough time, the entire universe will become observable. It won't. The universe is not just expanding, it's accelerating. Distant galaxies are moving away from us faster and faster, driven by something we call dark energy. At a certain distance, galaxies are receding faster than the speed of light, not through space, which would violate relativity, but because space itself is expanding faster than light can cross it. Those galaxies are beyond what's called the cosmic event horizon. Light leaving them today will never reach us, ever, even if we wait forever. The expansion of space will always outrun the light, and as time goes on, more and more galaxies will cross that threshold and disappear from view, not because they're destroyed, but because the space between us and them is growing too fast for light to ever close the gap. Billions of years from now, an astronomer on Earth, assuming Earth still exists and anyone is still around to look up, will point a telescope at the sky and see far fewer galaxies than we see today. The universe will look emptier, not because galaxies are dying, but because they've drifted beyond the horizon. Eventually, in the far future, trillions of years from now, the only galaxies left in the observable universe will be the ones gravitationally bound to our local group. Everything else will have receded beyond reach. An observer in that distant future would look out and see a quiet, dark, nearly empty cosmos. They would have no way of knowing that billions of galaxies once filled the sky. The evidence will have vanished over the horizon, carried away by the expansion of space. So the 93 billion light-year boundary is not a permanent feature of the universe. It's a snapshot, a measurement of how far light has traveled and how much space has expanded up to this moment. In the past, the observable universe was smaller. In the future, it will be larger for a while, and then effectively smaller as galaxies drift beyond the event horizon and stop sending us light. The visible frontier is shifting constantly, and we are trapped inside it, watching the universe reveal itself one photon at a time while the rest of it slips away into the dark. That is the observable universe. A sphere 93 billion light-years across, centered on you, bounded by the speed of light and the age of the cosmos, defined not by where the universe ends, but by how far we can see. It is not the whole universe, it is just the part we have access to. And every number, Every distance, every galaxy we've ever catalogued sits somewhere inside that bubble. Outside it, the universe continues. Unobserved, unmeasured, unknowable. And the thing that drew that boundary, the thing that made the visible frontier what it is not a wall or a limit in space. It's a process, a relentless, accelerating expansion that has been stretching the universe since the first moment it existed. That expansion is the invisible engine, and it's been running for 13.8 billion years without stopping. Space is stretching. Right now, at this exact moment, the distance between galaxies is increasing. Not because galaxies are flying through space like bullets, but because space itself, the fabric of the universe, is expanding. The ground is growing, the stage is getting bigger, and everything standing on it is being pulled apart by a force that nobody predicted, nobody expected, and nobody fully understands. This is the invisible engine, the mechanism that turned a hot, dense point 13.8 billion years ago into a universe 93 billion light-years wide. It has been running since the first fraction of a second after the Big Bang, and it shows no sign of stopping. In fact, it is speeding up. And the implications of that acceleration are so strange, so unsettling, that even scientists who have spent their entire careers studying it will admit they do not have a clean answer for what is actually happening. The story starts in 1929 with a man named Edwin Hubble. Not the telescope, the astronomer the telescope was named after. Hubble was working at the Mount Wilson Observatory in California, using what was at the time the most powerful telescope in the world. He was measuring the distances to galaxies and comparing those distances to how fast the galaxies were moving. The motion part was relatively easy to measure. When an object in space is moving away from you, the light it emits gets stretched. The wavelengths shift toward the red end of the spectrum. Astronomers call this redshift. The faster something is moving away, the more its light is redshifted. By analyzing the light from distant galaxies, Hubble could calculate how fast they were receding. The distance part was harder. To figure out how far away a galaxy is, you need a standard candle, something with a known brightness that you can spot inside the galaxy. Hubble used Cepheid variable stars, which pulse at a rate that correlates directly with their true luminosity. Measure the pulse, calculate the brightness, compare it to how dim the star looks from Earth, and you have a distance. It is not perfect, but it works. Hubble measured distances to 24 galaxies, plotted them against their recession speeds, and found something no one expected. The farther away a galaxy was, the faster it was moving away from us. Not a loose trend, a clean linear relationship. Double the distance and the speed doubles. Triple the distance and the speed triples. The universe was not static, it was expanding. And the expansion was uniform in every direction. This was not supposed to happen. Albert Einstein had published his general theory of relativity in 1915, and the equations predicted that the universe should either be collapsing under its own gravity or expanding. Einstein did not like that. He believed the universe was eternal and unchanging, so he added a term to his equations called the cosmological constant, a kind of repulsive force that would hold the universe in balance. When Hubble published his results, Einstein reportedly called the cosmological constant the biggest blunder of his life. The universe was expanding. The math had predicted it. The observations confirmed it. And Einstein had ignored his own equations because he did not like what they implied. Hubble's discovery became known as Hubble's law. It states that the velocity at which a galaxy is receding from us is proportional to its distance. The constant of proportionality is called the Hubble constant, and it tells you how fast the universe is expanding. Measure the constant, and you can calculate the age of the universe. the size of the observable universe, and the rate at which galaxies are drifting apart. For decades, astronomers argued over what the true value of the Hubble constant was. Early estimates were wildly wrong. Some made the universe appear younger than the Earth. Others made it twice as old as it actually is. By the 1990s, the number had settled into a range most scientists could agree on, somewhere around 70 kilometers per second per megaparsec. A megaparsec, for reference, is about 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are moving away from you about 70 kilometers per second faster. That number has consequences. If galaxies are moving apart at a steady rate, you can run the clock backward and figure out when they were all in the same place. Do the math, and you get an age for the universe of roughly 13.8 billion years. The expansion also means that space itself is growing. Galaxies are not flying through space. Space is carrying them. Picture a balloon with dots drawn on its surface. Inflate the balloon and the dots move apart. None of the dots are moving across the surface of the balloon. The surface itself is expanding, and the dots are being pulled along with it. The universe works the same way, except in 3 dimensions instead of 2. Space expands, galaxies follow. The farther apart 2 galaxies are, the more space there is between them, and the faster that space is expanding. Here is where it gets uncomfortable. At large enough distances, galaxies are receding from us faster than the speed of light. That sounds like a violation of relativity. It is not. Nothing is moving faster than light through space. But space itself can expand as fast as it wants. There is no speed limit on the stretching of space. A galaxy 14 billion light-years away is not traveling through space at faster than light speed. The space between us and that galaxy is expanding so quickly that the distance grows faster than light can cross it. The galaxy is standing still in its local patch of space. We are standing still in ours, but the ground between us is growing at a rate that makes the effective recession speed faster than light. This is not a theory, it is an observation. We can see galaxies whose light has been so severely redshifted that they must be receding at superluminal speeds. The light we are receiving from them was emitted billions of years ago when they were much closer and the recession speed was slower. The light has been chasing us ever since, fighting against the expansion of space, and only now, after billions of years, has it finally reached us. By the time the light arrives, the galaxy that sent it is vastly farther away than it was when the photons left, and it is still moving away, faster than light, completely unreachable. So the universe is expanding, space is stretching, galaxies are drifting apart. For most of the 20th century, scientists assumed the expansion was slowing down. Gravity, after all, pulls things together. The matter in the universe should be acting as a brake on the expansion, gradually reducing the rate over time. Eventually, the thinking went, the expansion might slow enough that gravity takes over and the universe begins to collapse back in on itself, ending in a big crunch. Or maybe the expansion would slow asymptotically, approaching but never quite reaching zero. Either way, the universe was expected to decelerate. That assumption held until 1998, when 2 independent teams of astronomers made a discovery that flipped the entire field on its head. Both teams were studying Type 1a supernovae, exploding stars that serve as extremely reliable distance markers. A Type 1a supernova occurs when a white dwarf star pulls material from a companion star until it reaches a critical mass and detonates. Because the mass at detonation is always the same, the explosion is always the same brightness. Spot one in a distant galaxy, measure how dim it looks from Earth, and you can calculate how far away it is. Compare that distance to the galaxy's redshift, and you get a measurement of how fast the universe was expanding at that earlier time. The teams expected to find that distant supernovae were slightly brighter than predicted, indicating that the universe was decelerating. Instead, they found the opposite. The supernovae were dimmer than expected. That meant they were farther away than they should be if the universe were slowing down. The only explanation was that the universe was not decelerating. It was accelerating. This was not a small adjustment. It was a complete reversal of the expected behavior. Something was pushing galaxies apart, overcoming the attractive pull of gravity, and driving the expansion faster and faster. The discovery won the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011, and it left cosmologists scrambling to explain what was causing the acceleration. They gave the unknown force a name: dark energy. The name is a placeholder. Dark does not mean it is made of anything shadowy or sinister. It just means we have no idea what it is. Energy refers to the fact that whatever it is, it behaves like a form of energy spread throughout space. The more space there is, the more dark energy there is. As the universe expands, the amount of dark energy increases, which drives the expansion even faster. It is a runaway process. Expansion creates more space. More space creates more dark energy. More dark energy drives faster expansion. Dark energy is not a substance. It is not particles you can detect or waves you can measure. It is a property of space itself. Every cubic meter of empty space contains a tiny amount of dark energy. That amount is so small that it has virtually no effect on anything happening at human scales or even galactic scales. But across the vast distances between galaxy clusters, where space itself is the dominant thing, dark energy adds up, and it pushes. The current leading explanation for what dark energy might be is Einstein's old cosmological constant, the same term he added to his equations in 1915 and later called his biggest blunder. It turns out he was not wrong to include it. He was just wrong about why it was there. The cosmological constant represents a baseline energy density of empty space, a kind of vacuum energy that does not dilute as the universe expands. It is always there, always the same strength per unit volume, and it always pushes outward. If the cosmological constant is the correct explanation, then dark energy is built into the fabric of space itself. It is not a force that was added later. It has been there since the beginning. In the early universe, when everything was much closer together, the density of matter and radiation was so high that their gravitational pull dominated. The expansion was decelerating. But as the universe grew and the density of matter dropped, dark energy started to win. Somewhere around 5 billion years ago, the expansion shifted from decelerating to accelerating. Today, dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, makes up another 27%. Normal matter, the stuff of stars and planets and people, makes up less than 5%. We live in a universe dominated by things we cannot see and do not understand. The acceleration has implications that stretch far into the future. Right now, we can observe galaxies that are roughly 46 billion light-years away. Light from those galaxies is still reaching us, stretched by billions of years of expansion, but arriving nonetheless. As time goes on, more distant regions of space will come into view. Light that has been traveling for 8 billion years will have traveled for 14 billion years, then 15 billion, then 20 billion. The particle horizon will expand. The observable universe will grow. But here is the catch. The acceleration means that galaxies beyond a certain distance are receding so fast that their light will never reach us, ever, even if we wait forever. The expansion of space between us and them is growing faster than the light can travel. Those galaxies are beyond what astronomers call the cosmic event horizon, and as the universe continues to accelerate, more and more galaxies will cross that threshold and disappear from view. Not all at once, not tomorrow, but over billions of years, the observable universe will become emptier. Galaxies that are currently visible will drift beyond the event horizon. Their light will redshift further and further until the photons are stretched to wavelengths so long that no detector will ever pick them up. Eventually, the only galaxies left in the observable universe will be the ones gravitationally bound to our local group: the Milky Way, Andromeda, Triangulum, and a few dozen smaller galaxies. Everything else will be gone, carried away by the expansion of space into a region we can never observe. An astronomer trillions of years in the future, assuming anyone is still around to look, would point a telescope at the sky and see almost nothing: a handful of nearby galaxies. No distant clusters, no cosmic web, no evidence that the universe was ever filled with hundreds of billions of galaxies. The information will have been erased by expansion. That future astronomer would have no way of knowing that the universe is 93 billion light-years wide. They would not be able to measure the Hubble constant by observing distant galaxies because there would be no distant galaxies to observe. They would not see the cosmic microwave background stretched into invisibility by trillions of years of expansion. The universe they observe would look small, quiet, and static. They would be wrong, but they would have no data to tell them otherwise. The evidence would be gone. In a very real sense, we are living in a special time, a window of cosmic history where the universe is old enough to have formed complex structures, but young enough that we can still see the distant past. We can measure the expansion. We can detect the cosmic microwave background. We can observe galaxies as they existed billions of years ago. Future civilizations will not have that luxury. The universe will have expanded so much that the evidence of its own history will be out of reach. Let's talk about the speed, because 670 million miles per hour is a number that gets thrown around when people try to describe how fast space is expanding. That number is real, but it needs context. It does not mean space is moving at 670 million miles per hour everywhere. It means that, at a specific distance, the recession speed due to expansion reaches that value. The farther out you look, the faster the recession speed becomes. At twice that distance, the speed is twice as high. At 10 times the distance, 10 times the speed. There is no upper limit. Space can expand as fast as it wants, because space is not a thing that moves. It is the thing that defines what movement is. The 670 million miles per hour figure is just a benchmark, a way of converting the Hubble constant into units that feel more tangible. But the reality is stranger and less intuitive than any single speed can capture. Here is another way to think about it. Imagine two galaxies sitting 10 million light-years apart. The space between them is expanding. After a certain amount of time, they are now 10,000,001 light-years apart. Neither galaxy moved. Space grew. Now imagine two galaxies 100 million light-years apart. The same amount of time passes, but now the distance between them has grown by 10 light-years instead of 1. 10 times the distance, 10 times the expansion. The expansion rate is constant per unit distance, but the total amount of new space created depends on how much space there was to begin with. The farther apart two objects are, the more space there is between them, and the more new space gets created. That is why distant galaxies recede faster. It is not because they are being pushed harder. It is because there is more space between us and them, and all of that space is expanding at the same rate. The acceleration adds another layer. Not only is space expanding, but the rate of expansion is increasing over time. 1 billion years ago, the Hubble constant was slightly smaller than it is today. 1 billion years from now, it will be slightly larger. Dark energy is pulling the accelerator pedal down, and the universe is responding by expanding faster and faster. This is not a linear process, it is exponential. The more the universe expands, the more dark energy there is. The more dark energy there is, the faster the universe expands. And there is no known mechanism that will stop it. The universe is not headed for a big crunch. It is headed for something much stranger. Some cosmologists call it the Big Rip. Others call it heat death. Either way, the long-term forecast is cold, dark, and empty. But that is trillions of years away. For now, the expansion is slow enough that structures held together by gravity, stars, galaxies, galaxy clusters, are not being torn apart. The Milky Way is not expanding. The solar system is not expanding. You are not expanding. Gravity is strong enough at those scales to hold things together. It is only at the largest scales, across the voids between galaxy superclusters, that the expansion dominates, and that is where the invisible engine does its work. Quietly, relentlessly, stretching the universe larger every second, adding new space to the gaps, pushing the horizons farther away, creating a cosmos that is simultaneously growing and becoming less observable. So Hubble's law was not just a discovery about motion, it was a discovery about the nature of space itself. Space is not a fixed stage where events happen. It is a dynamic participant. It expands. It carries matter with it. It grows faster in some regions than others, depending on how much space there is to begin with. And somewhere in the fabric of that space, woven into every cubic centimeter of the vacuum, is an energy we cannot see, cannot measure directly, and cannot explain. An energy that has been driving the universe apart for billions of years and shows no sign of slowing down. That is the invisible engine, and it has been running since the moment the universe began, shaping everything that came after. And the light from those earliest moments, stretched and distorted by nearly 14 billion years of that expansion, is exactly what the James Webb Space Telescope was built to find. We built a telescope to look backward through time. That is not a metaphor. It is a literal description of what the James Webb Space Telescope does. Every photon that hits its mirror is a fossil, a signal from the past, carrying information about a moment that ended billions of years ago. Point Webb at a distant galaxy, and you are not seeing that galaxy as it is today. You are seeing it as it existed when the light left, back when the universe was younger, smaller, hotter. The farther out Webb looks, the farther back in time it sees, and in the last few years, it has seen farther back than any instrument in history. Webb launched on Christmas Day 2021, folded up inside an Ariane 5 rocket, riding a controlled explosion out of Earth's atmosphere and into deep space. It did not go into orbit around Earth. It traveled outward, past the Moon, to a point called the second Lagrange point, about 1.5 million kilometers from our planet. At that spot, the gravitational pull of Earth and the Sun balance in just the right way that Webb can sit there, relatively stable, without burning fuel to hold its position. It is cold out there, dark, perfect for infrared astronomy. Infrared is the key. Visible light is what human eyes detect, a narrow slice of the electromagnetic spectrum ranging from red to violet. But visible light is only a tiny fraction of what the universe is broadcasting. Most of the light in the cosmos has been stretched by expansion into longer wavelengths. Light that left a distant galaxy as ultraviolet or visible blue has been redshifted so far that by the time it reaches us, it arrives in the infrared. If you want to see the earliest galaxies, the ones that formed when the universe was still an infant, you need a telescope that can detect infrared light. Hubble could do some of that, but only at the shorter end of the infrared range. Webb was built to go deeper. Webb's primary mirror is 6.5 meters across, made of 18 hexagonal segments coated in a thin layer of gold. Gold reflects infrared light better than almost any other material. Each segment is independently adjustable, aligned with nanometer precision so that the entire mirror acts as one enormous collector. Behind the mirror sits a suite of instruments, cameras, spectrographs, coronagraphs, each one designed to pull information out of the faint infrared glow of the distant universe. And between the mirror and the sun sits a tennis court-sized sunshield made of 5 layers of metallized plastic. The sunshield keeps the hot side, the side facing the sun and earth, at around 300 Kelvin. The cold side, where the instruments live, sits at around 40 Kelvin. Cold enough that the telescope's own heat does not overwhelm the faint signals it is trying to detect. The first images came back in July 2022, and they were everything astronomers had hoped for. Sharp, detailed, flooded with galaxies that Hubble had barely been able to see or missed entirely. One of the earliest deep-field images, a patch of sky near a galaxy cluster called SMACS 723, revealed thousands of galaxies in a region no bigger than a grain of sand held at arm's length. Most of those galaxies are billions of light-years away. Some are so distant that their light has been traveling for more than 13 billion years. We are seeing them as they existed when the universe was less than 1 billion years old. Infrared astronomy does something visible light cannot. It sees through dust. The early universe was full of it. Dust clouds thick enough to block visible light completely. Stars forming inside those clouds would be invisible to a telescope like Hubble. But infrared light passes through dust relatively easily. Webb can peer through the murk and detect the heat signature of stars igniting, galaxies assembling, black holes feeding. It is like having X-ray vision for the cosmos. The stuff that used to hide things is now transparent. One of Webb's first major discoveries was a galaxy called Jade's GSZ 13-0. The name is a mouthful. JADES stands for JWST Advanced Deep Extragalactic Survey, a coordinated program designed to push the telescope to its limits. The Z13 part refers to its redshift, a measure of how much the light has been stretched. A redshift of 13 means the light has been stretched by a factor of 14. The galaxy is so far away that we are seeing it as it existed roughly 13.4 billion years ago, only about 300 million years after the Big Bang. That is early, shockingly early. Before Webb, the farthest confirmed galaxies were seen at redshifts around 11 or 12. Webb blew past that within months. Jade's GSZ 13-0 is not alone. Webb has found dozens of galaxies at similar distances, some of them massive, some of them bright, all of them existing at a time when the universe was supposed to still be getting its act together. The Standard Model predicted that galaxies in this era would be small, dim, chaotic. The first stars were just beginning to form. Heavy elements had not yet been forged in significant amounts. The universe was still mostly hydrogen and helium. Galaxies should have taken time to grow, hundreds of millions of years to pull themselves into anything resembling order. And yet, here they are, big galaxies, organized galaxies, galaxies that look disturbingly mature for their age. Some of these galaxies are so bright that their light output rivals galaxies billions of years older. That should not be possible. Brightness comes from stars, lots of stars. Building that many stars takes time. You need gas clouds to collapse. You need the first generation of stars to live and die, seeding the surrounding space with heavier elements. You need those enriched clouds to form a second generation of stars, then a third. Each cycle takes tens of millions of years at least. Run the numbers, and there is not enough time between the Big Bang and 300 million years later to build some of the galaxies Webb is finding. And yet there they are, sitting in the data, refusing to go away. The discoveries have forced cosmologists to revisit their models. Maybe star formation in the early universe was faster than we thought. Maybe the first clouds of gas collapsed more efficiently. Maybe dark matter, the invisible scaffolding that holds galaxies together, clumped together more aggressively in the early universe than current models allow. Or maybe something stranger is happening. Some of the brightest objects Webb has found might not be galaxies full of stars at all. They might be quasars, supermassive black holes feeding on infalling gas, heating it to millions of degrees, and outshining entire galaxies in the process. If that is the case, the question shifts. How did black holes that massive form so quickly? There is not enough time for a stellar mass black hole, the kind that forms when a massive star collapses, to grow to a billion solar masses by eating nearby gas. The math does not work. Not in 300 million years, not even if the black hole is feeding as fast as physics allows. One possibility is called direct collapse. In this scenario, giant clouds of primordial gas in the early universe skipped the star formation phase entirely and collapsed straight into black holes weighing tens or hundreds of thousands of solar masses. Start with a seed that large and you have a head start. Grow from there and you can reach billions of solar masses in the time available. It is speculative. No one has directly observed a direct collapse black hole, but it is one of the few ideas that can explain how supermassive black holes existed so early in the universe. Webb is not solving these mysteries yet. It is making them sharper. Every new observation adds detail. Every spectrum reveals another chemical fingerprint. Every deep field image finds more galaxies that should not be there. The telescope is doing exactly what it was designed to do. It is showing us what the early universe actually looked like, not what we thought it should look like. And the two do not match. Now go farther back, past the galaxies, past the first stars, past the moment when light could travel freely through space, back to a time when the universe was so hot and so dense that atoms could not hold themselves together. That era ended roughly 380,000 years after the Big Bang, and the light from that moment is still arriving, stretched by nearly 14 billion years of expansion. We call it the cosmic microwave background. The cosmic microwave background is not starlight, it is the afterglow of the Big Bang itself. When the universe was 380,000 years old, it was filled with a hot glowing fog of hydrogen plasma. Photons could not travel more than a short distance before bouncing off a charged particle. The universe was opaque. Then it cooled. Protons and electrons combined into neutral hydrogen atoms. Suddenly, photons could move without interference. The universe became transparent. The light that was freed at that moment has been traveling ever since, stretched by expansion from visible and ultraviolet wavelengths all the way into the microwave range. Today, that light fills the entire sky. It is faint, just a few degrees above absolute zero, but it is everywhere. Every direction you point a sensitive radio telescope, you detect it, a uniform glow coming from every point in the sky. The cosmic microwave background is the oldest light in the universe. It is also the most important. The CMB was discovered by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey. They were calibrating a large horn antenna and kept picking up a persistent background noise they could not explain. They thought it might be interference from nearby New York City. It was not. They thought it might be bird droppings inside the antenna. They cleaned it out. The noise did not go away. Eventually, they realized they were detecting radiation coming from space itself. The signal was the same in every direction. It had a temperature of about 3 Kelvin. It matched the predicted signature of the Big Bang's afterglow almost perfectly. Penzias and Wilson won the Nobel Prize for the discovery. They had found the echo of creation. The CMB is not perfectly smooth. If it were, the universe today would be perfectly smooth too. No galaxies, no stars, no structure. Just a uniform soup of hydrogen spreading outward forever. The CMB has tiny fluctuations, hot spots and cold spots that differ in temperature by only a few millionths of a degree. Those fluctuations are the seeds of everything that came later. Regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter. Over hundreds of millions of years, those overdense regions collapsed into the first stars, the first galaxies, the first clusters. The pattern of fluctuations in the CMB is a snapshot of the universe's initial conditions, a map of the density variations that would eventually grow into the cosmic web. NASA launched a satellite called COBE in 1989 to map the CMB in detail. It confirmed that the fluctuations were there. In 2001, a more advanced satellite called WMAP produced a much sharper map. And in 2009, the European Space Agency launched Planck, the most precise CMB observatory ever built. Planck's map of the cosmic microwave background is one of the most important images in all of science. It shows the entire sky color coded by temperature. The variations are tiny, but they are real. And embedded in those variations is information about the universe's age, its composition, its geometry, and its fate. From the CMB, cosmologists have determined that the universe is flat, not flat like a pancake. Flat in the sense that parallel lines stay parallel forever. If you drew two laser beams pointing in the same direction and let them travel across the universe, they would never converge or diverge. That flatness tells us that the total energy density of the universe is almost exactly equal to a critical value. Any higher and the universe would be closed, destined to collapse back in on itself. Any lower and it would be open, expanding forever, with space curving outward like a saddle. Ours is right on the edge, flat, infinite, as far as we can tell. The CMB also tells us what the universe is made of. About 68% dark energy, 27% dark matter, less than 5% normal matter, the stuff of stars and planets and people. We are a rounding error. The fluctuations in the CMB also give us the Hubble constant, the rate at which the universe is expanding. Planck's measurement gave a value of about 67 kilometers per second per megaparsec. That number has caused arguments, and we have already covered why. But the point here is that the CMB lets us measure fundamental properties of the universe by looking at light that has been traveling for more than 13 billion years. The cosmic microwave background is the farthest back in time we can see using light. Before that moment, the universe was opaque. Photons could not travel freely. Any light emitted before 380,000 years after the Big Bang got scattered and absorbed before it could go anywhere. It is like trying to see through fog. The fog is too thick. There is no window into the universe before the CMB, at least not with light. Gravitational waves might offer a way in, neutrinos might, but photons, the particles that make up light, hit a wall. The cosmic microwave background is that wall. It is the surface of last scattering, the edge of the visible past. So Webb sees galaxies forming 300 million years after the Big Bang. The CMB shows us the universe at 380,000 years after the Big Bang. Between those two observations lies a period astronomers call the Cosmic Dark Ages. No stars had formed yet, no galaxies. The universe was dark, filled with cooling neutral hydrogen gas, slowly clumping together under the pull of gravity. This era lasted for tens or hundreds of millions of years, depending on where you were. Eventually, the densest clumps of gas collapsed and ignited the first stars. Astronomers call them population 3 stars. They were massive, hundreds of times the mass of the Sun, hot, blue, short-lived. They burned hydrogen into helium, helium into carbon, carbon into oxygen, building heavier elements in their cores. Then they exploded. The supernova seeded the surrounding gas with the first heavy elements in the history of the universe. From those enriched clouds, the next generation of stars formed, smaller, longer-lived, more like the stars we see today. We have never directly observed a population 3 star. They are too far away and too faint, but Webb is looking. One of its major science goals is to find the signature of those first stars, either individually or as part of the earliest galaxies. The spectrum of a population 3 star would be distinct, no heavy elements, just hydrogen and helium. If Webb finds one, it will be the oldest star ever observed, a relic from the first light of the cosmos. The Dark Ages ended when the first stars turned on. Their ultraviolet light began ionizing the surrounding hydrogen, turning it from neutral back into plasma. The process is called reionization, and it took hundreds of millions of years. By the time the universe was about 1 billion years old, reionization was mostly complete. The universe was transparent again, but for a different reason. Instead of being too hot for atoms to form, like it was before the CMB, it was now filled with ionized gas, kept that way by the light from billions of stars. Reionization marks the end of the Dark Ages and the beginning of the era we can observe with telescopes like Webb. So here is the timeline. The Big Bang happens. The universe expands and cools. At 380,000 years, it becomes transparent. The CMB is released. The universe enters the Dark Ages. No stars, just hydrogen. At some point between 100 million and 300 million years, the first stars form. Reionization begins. By 1 billion years, the universe is full of stars and galaxies. Webb is observing the tail end of this process. The galaxies it sees at redshift 13 are among the earliest to form. They are not the first stars. Those are still hiding, but they are close. And every observation Webb makes brings us closer to seeing the moment the universe woke up. There is a limit to how far back we can see, and it is not the Big Bang. The Big Bang itself is not an event you can observe. It is a singularity, a breakdown in the equations, a moment where the laws of physics as we understand them stop making sense. The observable past begins at the moment the universe became transparent. Before that, there is no light to observe. Before the CMB, we are working from models and indirect evidence, not direct observation. The earliest fraction of a second after the Big Bang is described by theories like cosmic inflation, a period when the universe expanded faster than light for a brief moment, smoothing out irregularities and setting the stage for everything that followed. Inflation explains why the universe is flat. It explains why the CMB looks so uniform. It explains the origin of the density fluctuations that became galaxies. But we have no direct evidence that inflation happened. It is a model that fits the data, not a thing we have observed. Some physicists are working on ways to test inflation. Gravitational waves from the inflationary era might still be rippling through space, too faint to detect directly, but potentially leaving an imprint on the polarization of the CMB. Experiments like BICEP and the upcoming Lightbird satellite are searching for that signal. If they find it, it will be the first direct evidence of what happened in the first trillionth of a second after the Big Bang. If they do not, cosmologists will have to rethink the entire framework. Webb is not looking at inflation. Webb is looking at galaxies, stars, black holes, the structures that formed long after the inflationary era ended. But every galaxy Webb finds, every spectrum it captures, adds a piece to the puzzle. The early universe is no longer a blank space in our models. It is becoming a detailed map. We know what galaxies looked like at 300 million years, at 500 million years, at 1 billion years. We know how star formation rates changed over time. We know when the first heavy elements appeared. We know when supermassive black holes started growing. The timeline is filling in, the story is coming together, and the story is stranger than anyone expected. Galaxies formed faster, black holes grew bigger, stars ignited earlier. The universe was not a slow, orderly process. It was chaotic, violent, efficient. The first billion years of cosmic history were a frenzy of activity, and the evidence is sitting in Webb's data archives right now. Astronomers are still sorting through it. Every new deep-field image reveals more galaxies. Every spectrum contains more surprises. Webb has only been operating for a few years. It is expected to last at least a decade, maybe longer if the fuel holds out. A decade of staring at the earliest galaxies. A decade of watching the cosmic dark ages end. A decade of pushing the boundary of the observable past closer and closer to the beginning. But there is still a gap between the CMB and the first galaxies. Between 380,000 years and 300 million years. A stretch of time where the universe existed, but we cannot see it. Not yet. Maybe not ever, at least not with light. That gap is the frontier, the edge of what we can observe directly, and beyond that edge lies the question that has been lurking since the beginning. If the observable universe is 93 billion light-years wide, and the universe beyond that is unobservable, what is out there? How much more universe is there? Is it infinite? Is it finite? Does the question even make sense? That is not a question Webb can answer. It is not a question the CMB can answer. It is a question that requires a different kind of thinking, a different kind of evidence, and that is exactly where the conversation goes next. There is a boundary to observation, not a wall you could touch, or a surface you could photograph, but a hard limit to how far light can travel in the time the universe has existed. Stand at the center of your own observable sphere, 93 billion light-years wide, and you are surrounded by everything you can ever hope to see. Stars, galaxies, the cosmic microwave background glowing faintly at the edge of time. And then nothing. Not darkness in the way you understand it, just the absence of information. No photons have arrived from beyond that boundary because there has not been enough time for them to get here. So the question stops being, what do we see, and starts being, what is actually out there? This is not a question science was designed to answer. Observation is the backbone of the scientific method. You look at something, measure it, test it, build a model that explains what you saw, and then you look again to see if the model holds. But if something is permanently beyond your ability to observe, the rules change. You cannot measure it. You cannot test it directly. You are left with logic, mathematics, and assumptions, which means you are guessing, even if the guesses are educated and grounded in the best physics we have. And the two main guesses, the two possibilities that cosmologists take seriously, are so fundamentally different that accepting one over the other changes what the word universe even means. The first possibility is that the universe is infinite. Not infinite in the vague poetic sense, where people say the possibilities are infinite or the stars go on forever. Infinite in the most literal, unforgiving sense. Endless, no edge, no boundary, no center. Space stretches outward in every direction without stopping, filled with galaxies, stars, planets, all the way to eternity. If this is true, then the observable universe, the 93 billion light-year bubble we live in, is not special. It is just one region among an infinite number of identical regions. Beyond the horizon, space looks the same. Same density of galaxies, same distribution of matter, same laws of physics. The only difference is that the light from those regions has not reached us yet. And depending on how fast space is expanding, it may never reach us. But it is there, real, physical, filled with structure, an endless continuation of what we already see. The second possibility is that the universe is finite. It has a size, a total volume. You could, in principle, measure it and get a number. That number would be unimaginably large, far bigger than the observable universe, but it would still be a number. Finite does not necessarily mean there is an edge in the sense of a wall or a barrier. The universe could be shaped in such a way that it curves back on itself. Travel far enough in one direction and you end up where you started, like walking around the surface of a sphere, no edge but still finite. A closed universe, bounded but without a boundary. If this is true, the observable universe is a piece of something larger but measurable. Space is real, but it does not go on forever. There is a total amount of it, and we are seeing a fraction. Both possibilities are consistent with everything we have observed so far. That is the uncomfortable part. The data does not prefer one over the other. Measurements of the cosmic microwave background, the most precise map we have of the early universe, suggest that space is flat. Parallel lines stay parallel. Triangles add up to 180 degrees. Flat space, in the context of general relativity, implies infinite space. If the universe were closed, curved back on itself like the surface of a sphere, we would expect to see a slight curvature in the geometry of the cosmos. We do not. The measurements say flat to within the margin of error, and flat, according to the math, means infinite. But the margin of error matters. The curvature could be so slight that we cannot detect it yet. A sphere large enough looks flat when you are standing on its surface. Earth looks flat from the ground. It took global navigation and high-altitude observation to prove it is round. The universe could be the same way. Curved, closed, finite, but so large that the curvature is invisible from our vantage point. If the total size of the universe is 1,000 times larger than the observable universe, or 1,000,000 times, or 1,000,000,000 times, we would not be able to tell the difference. The part we can see would look flat no matter what the true shape is. The measurements we have rule out a small closed universe. They do not rule out a very large closed universe. So the data leaves the door open to both answers. Cosmologists rely on something called the cosmological principle to make progress. It is an assumption, not a proven fact. The principle states that the universe is homogeneous and isotropic on large enough scales. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. No special locations, no preferred directions. If you could teleport to a random spot 100 billion light-years away, the universe there would look statistically identical to the universe here. Same kinds of galaxies, same density of matter, same expansion rate. The cosmological principle is baked into every major model of the universe. Without it, the equations become unmanageable. You would need different rules for different regions, and there is no way to test that. So cosmologists assume uniformity and build from there. The principle is not pulled out of thin air. It is based on observation. Within the observable universe, on the largest scales, the cosmos does look homogeneous and isotropic. Galaxies are not distributed randomly. They cluster together in groups. Groups cluster into superclusters. Superclusters form filaments stretching across hundreds of millions of light-years. But zoom out far enough, and those filaments smooth into a uniform distribution. The cosmic microwave background, which shows us the universe at 380,000 years old, is almost perfectly smooth. The temperature variations are tiny, only a few parts per million. That smoothness suggests the universe was uniform back then, and if it was uniform then, it is probably uniform now. And if it is uniform within the observable universe, the safest bet is that it stays uniform beyond the observable universe. But safe bets are not certainties. The cosmological principle is an assumption. A useful one, a reasonable one, but still an assumption. There is no way to prove that the universe beyond the horizon looks like the universe inside the horizon, because we cannot see it. The principle works as long as the universe is infinite, or as long as the finite universe is large enough that its boundaries are far beyond our reach. But if the universe has an edge, a real physical boundary where space ends, the principle breaks down at that boundary. And if the universe is not uniform beyond the horizon, if there are regions where the density is different or the laws of physics operate under different constants, the principle breaks down there too. We would have no way of knowing unless the effects of those differences somehow rippled into the observable universe. So far, no one has found convincing evidence of such effects, which means either the universe is uniform or the non-uniform parts are far enough away that they do not matter to us. Now let's talk about edges, because the idea of space having an edge is one of the hardest concepts in cosmology to wrap your brain around. If the universe is finite and has a boundary, what is on the other side of that boundary? The instinctive answer is nothing, empty space, a void. But that is not right. Space is not a container that holds things. Space is the thing. If space ends, there is no other side. There is no void beyond it. There is literally nothing. Not blackness, not emptiness, nothing. No dimensions, no time, no potential for anything to exist. The concept does not fit into human intuition because we are used to boundaries being edges between two regions. The edge of a table is where the table stops and the air starts. The shore is where the land stops and the ocean starts. But a boundary to space is not an edge between two things. It is the place where the concept of place stops meaning anything. General relativity allows for this. Einstein's equations describe space as a dynamic entity that can curve, stretch, expand, and in principle terminate. A finite universe in general relativity is not a ball of space sitting inside a larger void. It is a self-contained geometry. Space curves back on itself or simply ends, and there is no exterior. The mathematics works, the physics is consistent, but the implications are strange enough that even physicists who work with these models every day admit it feels wrong. Our brains evolved to navigate three-dimensional environments where every boundary has another side. A universe with no other side is not something we are wired to understand. So, what would an edge look like if you somehow reached it? The question is not quite fair because in most finite universe models, you cannot reach an edge. If space curves back on itself, traveling in one direction eventually brings you back to where you started. You would never hit a wall. You would just loop. But if there were a true boundary, an actual termination point, approaching it would be deeply strange. General relativity predicts that geometry breaks down at boundaries like that. Distances stop making sense. Time behaves unpredictably. You would not see a wall or a surface. You would see a region where the structure of space itself becomes undefined. Some models suggest that any matter approaching such a boundary would be unable to reach it. Space would stretch in such a way that the boundary stays forever out of reach, like trying to walk to the horizon on Earth. Others suggest the boundary would act like a singularity, a point where the equations fail and physics as we understand it stops applying. Either way, it is not something you could stand next to and touch. The finite universe models that avoid this strangeness are the ones where space is closed. Imagine the surface of a balloon. It is two-dimensional, finite in area, but has no edge. An ant walking on the surface could travel in any direction and never fall off. It would just keep walking and eventually end up back where it started. Now add a dimension. Instead of a two-dimensional surface, imagine a three-dimensional space that curves back on itself the same way. This is called a three-sphere, and it is one of the geometries general relativity allows for. A three-sphere universe is finite in volume but has no boundary. Travel far enough in one direction and you return to your starting point. The universe wraps around. If we live in a closed universe like that, the total size would determine whether we could ever detect the curvature. If the universe is only a few times larger than the observable universe, we might see repeating patterns in the distribution of galaxies. Look far enough in one direction and you start seeing the same structures you saw looking in the opposite direction because the light has wrapped around. Astronomers have searched for this. They have looked at the cosmic microwave background and the distribution of distant galaxies, checking for signs of a wrapped geometry. So far, they have found nothing, which means either the universe is flat and infinite or it is closed but so large that the curvature is undetectable. Current measurements allow for a closed universe as long as the total size is at least a few hundred times larger than the observable universe. Bigger than that, and we would never know the difference. So, where does that leave us? Two possibilities. Infinite or finite, both allowed by the data, both consistent with observation. The infinite universe is simpler in some ways, no edges, no special boundaries, just space going on forever, filled with galaxies, behaving the same everywhere. It fits the cosmological principle cleanly. It avoids the awkward question of what lies beyond a boundary, and the measurements of the cosmic microwave background favor it, at least slightly. But infinity comes with its own problems. An infinite universe means infinite matter, infinite stars, infinite galaxies, infinite planets. And if the universe is truly infinite and truly uniform, then somewhere out there, far beyond the observable horizon, there is another version of you. Not a metaphor, an actual copy, same atoms, same arrangement, same memories, reading these same words at this exact moment. Probability demands it. In an infinite universe with a finite number of possible configurations of matter, every configuration repeats eventually. You repeat, Earth repeats, the solar system repeats, everything repeats an infinite number of times. That conclusion bothers some people, it feels wrong, but the math does not care. If space is infinite and matter is distributed uniformly, then every possible arrangement of particles happens somewhere. Most of those arrangements are random noise, a cloud of gas, a scattered collection of atoms. But some of those arrangements are stars, planets, life, you. The probability of any specific arrangement is vanishingly small, but infinity is very large. Multiply a vanishingly small probability by an infinite number of trials, and the result is certainty. There is another you out there. Many other yous, infinite other yous in fact. Most of them are slightly different. Small variations in how the atoms came together. But some of them are identical down to the quantum state, perfect copies, living identical lives, making identical choices. The distance to the nearest identical copy depends on how many possible configurations there are, and that number is large, but not infinite. Estimates suggest the nearest identical region might be 10 to the power of 10 to the power of 115 meters away, a number so large it makes the observable universe look like a speck. But in an infinite universe, that distance is finite. The copy exists. The finite universe avoids this weirdness. If space has a total volume, there is a finite amount of matter, a finite number of galaxies, a finite number of stars, no duplicates. You are unique, not just in the observable universe, but in the entire universe. The trade-off is that you have to explain what finite means in a context where there is no outside. You have to accept that space itself has a size, a total amount, and that size is arbitrary. Why that size and not another? Why does space curve back on itself at this distance and not some other distance? The finite universe raises questions it cannot answer. The infinite universe gives answers some people wish it wouldn't. Both models agree on one thing. Whatever lies beyond the observable universe, whether it is infinite space or the far side of a closed geometry, it is not fundamentally different from what we see here. The laws of physics are the same. The types of particles are the same. The forces that govern matter operate the same way. The cosmological principle holds. Beyond the horizon is more universe, not a different kind of universe, just more of the same. Galaxies forming, stars dying, planets orbiting, all of it playing out in regions we will never observe. The universe beyond the edge of observation is not exotic. It is mundane, which is almost disappointing. There is a philosophical weight to this question that goes beyond the science. If the universe is infinite, then everything is diluted. Humanity is not just insignificant in the sense of being a small part of a large cosmos. Humanity is insignificant in the sense of being one instance among infinite instances. Your life, your choices, your existence, all of it is repeated infinitely many times, in infinitely many configurations. The meaning of uniqueness collapses. The meaning of consequence becomes murky. If every possible version of you exists somewhere, does it matter which version you are? If every decision you could make is made by some copy of you in some distant region, does free will mean anything? Philosophy has wrestled with these questions for centuries, but the infinite universe turns them from abstract thought experiments into potential descriptions of reality. If the universe is finite, the weight shifts. You are unique. Your choices are unique. There is no duplicate living out the alternate version of your life. The universe is large, but comprehensible. It has a size, a total inventory, a boundary, even if that boundary is not an edge in the traditional sense. Humanity is still a small part of a vast whole, but at least the whole is a measurable thing. You are not one instance among infinitely many. You are one instance, period. That distinction matters to some people. It should not matter to the physics. The equations do not care whether you feel significant. But humans are not equations. We think about what the universe means, not just what it is. And the difference between infinite and finite changes what it means. The question is unlikely to be answered anytime soon. The tools we have, telescopes, satellites, detectors, all of them are limited by the speed of light and the age of the universe. We cannot see beyond the observable horizon. We cannot measure the total size of the universe if that size is more than a few times larger than what we can see. Future observations might tighten the constraints. Better measurements of the cosmic microwave background might detect a curvature so slight that current instruments miss it. That would favor a finite closed universe. Or the measurements might confirm flatness to even higher precision, strengthening the case for infinity. But unless the universe is small enough that we can detect its curvature or its topology, the question stays open. We are left with models, assumptions, and probabilities. There is another angle, a way the question might become answerable even if we cannot see beyond the horizon. If the universe is not uniform, if there are regions where the density of matter is significantly different, or where the constants of physics vary, those differences might leave an imprint on the observable universe. Gravitational effects from a massive overdense region beyond the horizon could create anomalies in the cosmic microwave background. Variations in physical constants could produce unexpected patterns in the distribution of galaxies. Some researchers have claimed to find hints of such anomalies, a cold spot in the cosmic microwave background that is larger and colder than statistical fluctuations should allow. Alignments in the distribution of galaxy clusters that suggest a preferred direction in space, violating the assumption of isotropy. None of these claims have been confirmed. Most cosmologists think they are statistical flukes, the kind of thing that happens when you search large data sets for patterns. But if any of them turn out to be real, they would suggest that the universe beyond the observable horizon is not as uniform as the cosmological principle assumes, and that would open the door to a very different kind of answer. The infinite versus finite question is often framed as a binary. Either the universe goes on forever or it does not. But there is a third option that does not fit neatly into either category. The universe could be infinite in some directions and finite in others. Space could have a complicated topology. Imagine a shape like a torus, a donut. The surface of a torus is finite in one sense. It has a total area, but it wraps around in two independent directions. An ant walking on a torus could travel forward and eventually return to its starting point, or it could travel sideways and return, but the two loops are different lengths. Now extend that idea to 3 dimensions and add more complexity. Space could twist, fold, connect back to itself in unexpected ways. These topologies are mathematically consistent with general relativity, and some of them predict observable effects. If space wraps around at a scale comparable to the observable universe, we might see multiple images of the same galaxy in different directions, light that took different paths around the topology and arrived at Earth from different angles. Astronomers have searched for this. They have not found it, which means either the topology is too large to detect or space is simpler than these models allow. The simplest answer, the one most cosmologists default to, is that the universe is flat and infinite. It matches the data. It does not require complicated topology. It fits the cosmological principle without caveat. But simplicity is not proof. The universe has surprised us before. It surprised us with accelerating expansion. It surprised us with the existence of dark matter. It surprised us with galaxies forming faster than the models predicted. Every time we build a telescope powerful enough to see farther or measure more precisely, we find something that does not quite fit the story we were telling. The question of what lies beyond the observable universe is one of the biggest gaps in that story, and gaps are where the surprises live. So the honest answer is, we do not know. We have two main models: infinite space stretching forever, filled with galaxies and stars, and perhaps infinite copies of everything we see, or finite space, curved back on itself, or simply bounded, containing a measurable total amount of matter and structure. Both fit the data. Both are consistent with the laws of physics as we understand them. The choice between them comes down to interpretation, assumption, and what you are willing to accept about the nature of existence. Some scientists prefer the infinite model because it is simpler and avoids the question of boundaries. Others prefer the finite model because it keeps the universe comprehensible and avoids the philosophical baggage of infinite duplicates. Neither side has won the argument. But there is a way the question gets even stranger, a way that both answers, infinite and finite, might be too limited. Because what if the observable universe is not just a region within a larger universe? What if it is one bubble in a vast foam of universes, each with its own properties, its own laws, its own history? What if the thing we call the universe is just one pocket in something much larger and much stranger? That idea has a name. They call it the multiverse. And once you start taking it seriously, the question stops being what lies beyond our universe and starts being how many universes are there. That is not a question observation alone can answer, but it is the question cosmology is quietly, carefully starting to ask. What if the observable universe is not the universe? What if the 93 billion light-year sphere we have been mapping and measuring and theorizing about is just one room in a house with infinite rooms, not a metaphor, not a thought experiment, a literal description of the structure of reality, multiple universes, separate bubbles of space and time, each with its own laws, its own constants, its own history. Some of them might look like ours. Others might be so alien that matter as we understand it cannot exist. And all of them, according to this idea, are real, physical, out there somewhere, or maybe everywhere, depending on how you define location when space itself becomes plural. This is the multiverse hypothesis. And before you dismiss it as science fiction, understand that some of the most respected physicists alive take it seriously. Not as a fringe idea, not as speculation for late-night documentaries, as a legitimate possibility that emerges naturally from theories we already use to explain the universe we can see. The multiverse is not something anyone went looking for. It is something that fell out of the equations when cosmologists tried to solve a completely different problem, and once it showed up, it refused to go away. The problem was the early universe, specifically why the universe looked so uniform. The cosmic microwave background, that faint glow of radiation left over from 380,000 years after the Big Bang, is almost perfectly smooth. The temperature is the same in every direction to within a few parts per million. That uniformity is strange because regions of the early universe that are now on opposite sides of the observable universe were never in contact with each other. Light from one side had not had enough time to reach the other side. They were causally disconnected. So how did they end up at the same temperature? How did the entire universe coordinate itself into such a uniform state when no signal could have traveled fast enough to spread that information? The answer, proposed in the early 1980s by a physicist named Alan Guth, is called cosmic inflation. Inflation posits that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, not gradually, exponentially. The size of the universe doubled, then doubled again, over and over, in an incomprehensibly short time. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than an atom inflated to a size larger than the observable universe today. That rapid expansion smoothed out any irregularities. It stretched space so flat and so uniform that by the time inflation ended and normal expansion took over, the universe looked the same everywhere. Problem solved. Inflation explains the uniformity of the cosmic microwave background. It explains why space is flat. It explains the origin of the tiny density fluctuations that eventually grew into galaxies. For decades, inflation has been the leading explanation for the initial conditions of the universe. But inflation comes with a side effect, a consequence that nobody expected and that changes the entire framework of cosmology. If inflation happened, it probably did not happen just once. And it probably did not stop everywhere at the same time. In 1986, a physicist named André Linde developed a version of inflation called eternal chaotic inflation. Linde's model starts with a quantum field, a kind of energy that fills space, and assumes that field is subject to quantum fluctuations. In some regions, the field's energy is high, in others it is low. When the energy is high enough, inflation kicks in, and that region of space starts expanding exponentially. But quantum fluctuations do not stop. Even while one region is inflating, fluctuations in other parts of the field can trigger new rounds of inflation. The process does not end. Inflation keeps happening in different regions, spawning new expanding bubbles, each of which can spawn more bubbles. It is a runaway process. Once it starts, it never fully stops. Each bubble is a universe. Our observable universe is one such bubble. A region where inflation ended, space cooled, particles formed, and eventually stars and galaxies assembled. But beyond the edge of our bubble, space is still inflating. And beyond that, other bubbles are forming, each one a separate pocket of space and time where inflation has ended and normal physics has taken over. These bubbles do not touch in the way two soap bubbles touch. They are separated by regions of space that are still inflating, expanding so fast that no signal can cross from one bubble to another. Each bubble is causally isolated, a universe unto itself. This is the bubble universe model. It is not a fringe idea. It is a direct consequence of taking inflation seriously and applying quantum mechanics to the field driving inflation. The math works. The model explains the observations, and the conclusion is unavoidable. If inflation happened, it probably happened many times. If it happened many times, there are many universes. The multiverse is not something you add to the theory. It is something the theory produces whether you want it to or not. Now here is where it gets strange. Each bubble universe could have different properties. The laws of physics as we know them, the constants that determine how particles interact, the strength of fundamental forces, all of that might be fixed by the conditions in each bubble when inflation ended. In our universe, the electromagnetic force has a certain strength. Gravity has a certain strength. The mass of the electron is what it is. But in another bubble, those values could be different, slightly different, or wildly different, depending on how the quantum field settled. Some bubbles might have stronger gravity. Some might have no electromagnetic force at all. Some might have particles we have never imagined. The laws are not universal across the multiverse. They are local. Each universe gets its own rulebook. This idea ties into something called string theory, which we will get to in the next part of this story. But for now, the key point is this. The properties we think of as fundamental, the things that make our universe behave the way it does, might just be accidents. Random outcomes of a quantum process that played out in the first moments after our bubble formed. We think the laws of physics are universal because within our universe they are. But step outside, into another bubble, and the rules change. The constants change, the possibilities change. And most of those possibilities, the vast majority of them, would not allow for anything resembling life. Stars would not form. Atoms would not hold together. Chemistry would not work. Our universe is tuned, finely tuned, in ways that make complexity possible. Change the strength of gravity by a few percent, and stars either burn out too fast or never ignite. Change the mass of the electron and atoms fall apart. We live in a universe that, against enormous odds, happens to allow for galaxies, planets, and people. And the multiverse offers an explanation for why. Not because the universe was designed for us, because there are so many universes that every possible configuration exists somewhere. Most of them are dead, empty, structureless. We exist in one of the rare bubbles where the constants landed in a range that allows for life. Not because we are special, because in an infinite multiverse, every possibility gets tried. We are here because this is the kind of universe where here is a thing that can exist. That explanation is called the anthropic principle. The weak version just says we observe the kind of universe we do because if the universe were different, we would not be here to observe it. It is a tautology, but it is true. The strong version, the one that gets more controversial, says the universe appears fine-tuned because there are many universes, and we necessarily find ourselves in one of the rare ones that allows observers to exist. Critics of the anthropic principle argue that it is not really an explanation. It does not tell you why the multiverse exists, or why the constants in our universe have the specific values they do. It just says we got lucky. Proponents argue that it is the only explanation that does not require invoking something outside the system. You do not need a designer. You do not need a cosmic plan. You just need a lot of universes, and the statistics take care of the rest. So the multiverse solves two problems at once. It explains why the early universe was so uniform through inflation, and it explains why the constants of physics are so finely tuned through the anthropic principle and the sheer number of possible universes. But it creates a much bigger problem. If other universes exist, we cannot see them. By definition, they are beyond our observable horizon, separated by regions of space that are expanding faster than light. No signal from another universe can reach us, no light, no gravitational waves, no particles. We are permanently cut off, which means the multiverse, as a hypothesis, might be untestable. And in science, if you cannot test something, if you cannot make a prediction that observation could confirm or rule out, the question arises whether it is even science. That criticism has been around since the multiverse idea gained traction. Philosophers and some physicists argue that the multiverse is metaphysics, not physics. It is an interesting idea, maybe even a beautiful idea, but it does not make predictions we can check. You cannot point a telescope at the edge of the observable universe and detect another bubble. You cannot build an experiment that confirms inflation created other universes. The theory works in the sense that the math is consistent and it explains observations, but it does so by invoking entities, other universes, that we can never interact with. Some call that elegant, others call it a cop-out. Not everyone agrees the multiverse is untestable. Some researchers have pointed to potential signatures that could show up in our universe if it collided with another bubble in the distant past. A collision like that would leave an imprint in the cosmic microwave background, a kind of bruise in the temperature map, a circular region that is slightly hotter or colder than the surrounding areas, with a specific pattern that matches what you would expect from a bubble collision. Teams have searched for this. They have found a few anomalies, cold spots and hot spots, that do not fit the expected statistical distribution, but none of them have been confirmed as collision signatures. Most cosmologists think they are just noise, random fluctuations that happen when you look at a data set large enough. The search continues, but so far, no smoking gun. There is another version of the multiverse that does not rely on inflation or bubbles at all. It comes from quantum mechanics, specifically from an interpretation of quantum mechanics called the many worlds interpretation. This idea was proposed in 1957 by a physicist named Hugh Everett, and it says something so strange that even people who work with quantum mechanics every day have trouble wrapping their heads around it. Every time a quantum event happens, an event with multiple possible outcomes, the universe splits. All possible outcomes occur, not in the sense that one outcome happens and the others do not. In the sense that every outcome happens in a separate branch of reality, a separate universe. Here is how it works. You have a particle that can be in one of two states, spin up or spin down. In standard quantum mechanics, the particle is in a superposition, both states at once, until you measure it. When you measure it, the superposition collapses and you get one outcome, spin up, let's say. The many worlds interpretation says the superposition never collapses. Instead, the universe splits into two branches. In one branch, you measure spin up. In the other branch, you measure spin down. Both versions of you exist. Both are real. Both continue forward in time, completely unaware of the other branch. The splitting happens constantly. Every quantum event, every interaction, every moment, the universe branches and branches and branches. The number of parallel universes in this version of the multiverse is not just large, it is unimaginably, incomprehensibly vast. Every possible history plays out somewhere. Every decision you could have made, you did make, in some branch. Every outcome of every coin flip, every roll of the dice, every quantum fluctuation in the early universe, all of them happened. You are living in one branch of an infinite tree of realities. The many worlds interpretation is popular among certain physicists because it solves a problem called the measurement problem. In standard quantum mechanics, the act of measurement seems to have a special role. The superposition collapses when you observe it. But what counts as observation? What counts as measurement? Does it require a conscious observer? The equations do not say. Many worlds gets rid of the problem by saying there is no collapse. The wave function, the mathematical object that describes all possible outcomes, never collapses. It just keeps evolving, splitting into branches. Measurement is not special. It is just another quantum interaction that causes the universe to branch. You do not collapse the wave function. You become entangled with it, and the branching creates multiple versions of you, each seeing a different outcome. Critics of many worlds argue that it is absurdly extravagant. You are multiplying the number of universes beyond any reasonable limit just to avoid saying the wave function collapses. Every quantum event creates trillions upon trillions of new universes. That seems like a high price to pay for mathematical consistency. Supporters argue that it is actually the simplest interpretation. You take the equations of quantum mechanics, apply them universally without adding special rules for measurement, and many worlds is what you get. The extravagance is a feature, not a bug. Reality is that large, that complex, that wildly branching, and we only see one thread of it because we are embedded in one branch. The many worlds multiverse is different from the bubble universe multiverse. The bubbles are separated by space, regions of the cosmos that inflated separately and are now out of reach. The many worlds branches are separated by quantum superposition. They coexist in the same space, but they do not interact. You cannot travel from one branch to another because the branches are not places, they are alternatives. Every point in space exists in every branch, but the state of that point, What particles are there, what they are doing, differs from branch to branch. The two versions of the multiverse are not mutually exclusive. Both could be true. You could have a multiverse of bubble universes, each with its own laws of physics, and within each bubble are many worlds branching of quantum outcomes, a multiverse of multiverses. If that idea makes your head hurt, you are not alone. Physicists who work on these problems every day still argue about what it all means, and the arguments are not just technical, they are philosophical. If there are infinite universes, does anything you do matter? If every choice you make is also made differently by another version of you in another branch, does the concept of choice even mean anything? If every possible outcome happens somewhere, what is the significance of the outcome that happens here? These are not idle questions. They are questions about the nature of reality, the meaning of existence, and the limits of what science can tell us. Some researchers embrace the weirdness. They argue that the multiverse, in whatever form it takes, is the natural conclusion of pushing our best theories to their logical endpoints. Inflation predicts eternal inflation. Eternal inflation predicts bubble universes. Quantum mechanics, taken seriously, predicts many worlds. You do not get to pick and choose which parts of the theory you like. If the math says there are other universes, then there probably are. Others push back. They argue that science is about explaining observations, not about following the math wherever it leads. If a theory predicts things we can never observe, that is a red flag. It might be mathematically elegant, but elegance is not the same as truth. The multiverse debate is as much about the philosophy of science as it is about cosmology or quantum mechanics. Here is a fact that might shift how you think about this. The multiverse hypothesis was not invented to make life interesting or to give philosophers something to argue about. It emerged because physicists were trying to solve concrete, well-defined problems. The uniformity of the cosmic microwave background, the flatness of space, the fine-tuning of physical constants, the measurement problem in quantum mechanics. Every one of those problems is real. Every one of them needs an explanation. And the multiverse, in its various forms, provides explanations that are consistent with the data and the math. That does not make it true, but it makes it serious, worthy of consideration, not dismissal. The word multiverse itself was coined by a psychologist named William James in 1895. He was not talking about cosmology. He was talking about philosophy, the idea that reality might be plural rather than singular. The term drifted through science fiction for most of the 20th century, showing up in comic books and novels, a fun idea with no real grounding. Then in the 1980s, it jumped from fiction to physics. Inflation gave it a mechanism. Quantum mechanics gave it a structure. String theory, which we will talk about next, gave it a landscape. And suddenly, the multiverse was not just a thought experiment. It was a hypothesis with equations behind it. One of the strongest proponents of the multiverse is a physicist named Max Tegmark. Tegmark has spent decades classifying different types of multiverses, organizing them into levels based on how they arise and what they imply. Level 1 is the simplest. It is just the idea that space goes on forever, and if space is infinite, then every possible arrangement of matter repeats somewhere. We covered that in the previous chapter. Level 2 is the bubble universe model. Different regions of space that inflated separately and are now causally disconnected. Level 3 is many worlds. Quantum branching, creating parallel realities. Level 4, the most speculative, is the idea that every mathematically consistent structure exists as a universe somewhere, not just different physical laws, different mathematics, different logic. That level is so abstract that even physicists who accept the other levels balk at it. But Tegmark argues it is the natural endpoint of taking the multiverse seriously. If reality is plural, why stop at different physical laws? Why not different mathematical structures entirely? Not everyone buys into Tegmark's classification, but it is a useful framework for thinking about how wild the multiverse idea can get. Each level adds another layer of strangeness. Each level expands the definition of what counts as real, and at every level the same question comes up. If we cannot observe it, if we cannot test it, does it count as science? Some say no, some say yes, as long as the theory that predicts the multiverse is itself testable. Inflation is testable. We can look for its signatures in the cosmic microwave background. Quantum mechanics is testable. We can run experiments in labs. If those theories predict a multiverse as a side effect, and the theories themselves hold up under observation, then the multiverse inherits their credibility. It is a secondary prediction, but it is still grounded in science. There is one more implication worth sitting with. If the multiverse is real, then the universe we observe, the 93 billion light-year bubble filled with galaxies and stars and us, is not special. It is not the universe. It is a universe. One bubble in an infinite foam, one branch in an infinite tree. Everything we have ever studied, every star we have catalogued, every distant galaxy Webb has photographed, all of it is local, specific to our patch of reality. The laws we have discovered, the constants we have measured, the structures we have mapped, none of it applies beyond our horizon. Other bubbles have other laws, other branches have other outcomes. The universe is not a singular thing with a singular set of rules. It is a collection, possibly infinite, of separate realms, most of which we will never see. That is either the most exciting idea in the history of science or the most frustrating. Exciting because it expands the scope of reality beyond anything humans have ever imagined. Frustrating because it places most of that reality permanently out of reach. We are trapped in our bubble, stuck in our branch. And no matter how far we travel or how long we wait, we will never cross into another universe. The boundaries are not walls we can break through. They are separations written into the structure of space and time itself. If the multiverse is real, we will spend the rest of history knowing that almost everything that exists is somewhere we can never go. But the multiverse hypothesis does something else. It shifts the question. Instead of asking what lies beyond the edge of our universe, we start asking what kind of structure could give rise to multiple universes. What is the substrate? What is the thing that contains all the bubbles or all the branches? Is there a higher dimensional space where our universe is just one object among many? Is space-time itself embedded in something larger? Those questions do not go away when you accept the multiverse. They get bigger. And the answers, if there are any, might not come from looking outward. They might come from looking inward, at the fabric of space itself, at the dimensions we can see and the ones we cannot, at the possibility that reality has more layers than we ever suspected. That is where the story goes next, not outward into other universes, inward into the structure of the one we are in. Because if space has hidden dimensions, if the fabric of reality is more complex than 3 dimensions and time, then the rules change, and everything we think we know about what is possible becomes negotiable. Reality might have more flaws than we thought. Not flaws in the sense of levels or tiers, flaws in the sense of actual spatial dimensions, directions you could move that are not forward, backward, left, right, up or down. Dimensions that exist right here, right now, woven into the fabric of space itself, but invisible to us because they are folded up so small or arranged in such a way that we cannot perceive them. This is not speculation in the casual sense. It is speculation grounded in mathematics, in theories that have been worked out in painstaking detail by physicists who are trying to solve very real, very concrete problems about how the universe operates. And the conclusion those theories keep arriving at is deeply strange. Space might not be three-dimensional. It might have 10 dimensions, or 11, or 26, depending on which version of the theory you are working with. Most of those dimensions are hidden, compactified, curled up into shapes so tiny that even particles moving through them do not notice. But they are there, and if they are there, they change everything. Let's start with what a dimension actually is, because the word gets used in science fiction to mean alternate realities or parallel worlds, and that is not what physicists mean when they talk about dimensions. A dimension is a direction, a degree of freedom, a way you can move through space. You live in 3 spatial dimensions. You can move left or right. That is one dimension. You can move forward or backward. That is a second dimension. You can move up or down. That is a third dimension. Those 3 directions are independent. You can combine them, move diagonally, move in curves, but every path you take can be described as some combination of movement along those 3 axes. Add time and you get 4 dimensions, 3 of space, 1 of time. That is the universe as we experience it, 4-dimensional space-time. You move through space and you move through time, and those 2 things are linked in ways that general relativity describes beautifully. But there is no law of physics that says space has to stop at 3 dimensions. The math allows for more. You can write down equations that describe spaces with 4 spatial dimensions, or 5, or 100. Those equations are consistent, they do not break. The question is whether those extra dimensions are real or just mathematical curiosities. For most of the 20th century, physicists treated higher dimensions as abstract tools, useful for certain calculations, but not physical. Then, in the 1970s and 80s, string theory emerged, and higher dimensions stopped being optional. They became necessary. String theory started as an attempt to unify the 2 great pillars of modern physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles at the smallest scales. Those 2 theories work beautifully in their own domains, but they do not play well together. When you try to combine them, when you try to describe gravity at the quantum level, the math explodes. You get infinities, nonsensical results, predictions that do not match reality. Physicists spent decades trying to fix this, and every attempt failed. Then someone had a strange idea. What if particles are not particles at all? What if they are tiny loops of vibrating string? In string theory, every particle in the universe, electrons, quarks, photons, all of them, is made of the same fundamental object, a string. A one-dimensional filament of energy so small that even our best particle accelerators cannot resolve it. The string vibrates, and the way it vibrates determines what kind of particle it appears to be. One vibration pattern looks like an electron, another looks like a quark, another looks like a photon. The particles we see are just different notes played on the same instrument. It is an elegant idea. One object, one fundamental building block, giving rise to the entire zoo of particles in the standard model. But the math of string theory only works in a specific number of dimensions, not 4, not 3 spatial dimensions plus time. String theory requires 10 dimensions, 9 spatial dimensions and 1 time dimension. If you try to build string theory in fewer dimensions, the equations fall apart. The symmetries do not hold, the infinities come back. 10 dimensions is not a choice, it is a requirement. The theory needs the extra space to function. And that immediately raises the obvious question: where are they? You are not aware of 6 extra dimensions. You cannot move through them. You cannot see them. You cannot point a direction and say that is the 5th dimension. The explanation string theory offers is called compactification. The extra dimensions are not large and open like the 3 we know. They are curled up, rolled into tiny shapes so small that they are effectively invisible. Imagine a garden hose. From a distance, the hose looks like a one-dimensional line, length but no width. But get close enough and you realize the hose has a second dimension: circumference. You can move along the length of the hose, which is obvious, but you can also move around the hose, circling its surface. That second dimension is there, but it only becomes apparent when you are close enough to see the hose's thickness. Now, shrink the hose down to a width far smaller than an atom. From any reasonable distance, it still looks like a one-dimensional line. The second dimension is there, but it is hidden by its size. String theory says the extra 6 dimensions are like that, curled up into tiny geometric shapes at every point in space, not just at specific locations, everywhere. Every point in the 3-dimensional space you can see has 6 additional dimensions folded into it, each one shaped like a complex geometric structure called a Calabi-Yau manifold. The manifolds are so small, somewhere around the Planck length, about 10 to the power of -35 meters, that particles moving through space do not notice them. The dimensions are there, but they are inaccessible. You cannot turn left into the 5th dimension because the 5th dimension is curled up so tightly that there is no room to move. The shape of those compactified dimensions matters a lot. The way the extra dimensions are curled determines how the strings vibrate, and the way the strings vibrate determines what particles exist and how they interact. Change the shape of the compactification and you change the physics. Different geometries give you different particles, different forces, different constants. String theory does not predict one unique universe. It predicts a vast landscape of possible universes, each corresponding to a different way the extra dimensions can be folded. Estimates suggest there are something like 10 to the power of 500 different possible compactifications. That is not a typo. 10 to the power of 500. A number so large that it makes the number of atoms in the observable universe look like a rounding error. Each of those compactifications is a valid solution to the equations, and each one gives you a different set of physical laws. This is both a strength and a problem. The strength is that the landscape explains the fine-tuning of physical constants in our universe. If there are 10 to the power of 500 possible universes, each with different constants, then somewhere in that landscape is a universe that looks like ours. We exist in one of the configurations where the constants happen to land in a range that allows for atoms, stars, galaxies, and life. It is the anthropic principle again, but now with a mechanism. The multiverse is not just a consequence of inflation. It is a consequence of the geometry of higher dimensions. The problem is that with 10 to the power of 500 possibilities, string theory does not make unique predictions. It does not tell you which compactification is ours. It does not tell you what the constants should be. It says they could be almost anything, depending on the shape of the extra dimensions, and that makes the theory hard to test. Critics of string theory have been vocal about this. If a theory predicts everything, it predicts nothing. If every possible outcome is allowed somewhere in the landscape, you cannot use the theory to make falsifiable predictions. You cannot rule it out. Some physicists argue that string theory has stopped being physics and become mathematics. Beautiful, elegant, internally consistent mathematics. But not science in the sense of making testable claims about the world. Supporters of string theory push back. They argue that the theory is still young, still being developed. Just because we have not found the right way to test it yet does not mean it is untestable. And they point to the fact that string theory is the only framework we have that successfully combines gravity and quantum mechanics without producing nonsense. That alone makes it worth pursuing. In the late 1990s, string theory evolved into something called M theory. The M stands for membrane, or maybe mystery, depending on who you ask. M theory unified 5 different versions of string theory that had been developed independently and showed that they were all different perspectives on the same underlying structure. And M theory added another dimension, not 10, 11, 10 spatial dimensions and 1 time dimension. The 11th dimension is different from the others. It is not compactified in the same way. It is a bulk dimension, and it opens the door to a very different picture of what the universe is. In M theory, our universe is not a collection of point particles or even vibrating strings. It is a brane, short for membrane, a 3-dimensional surface, a slice of space embedded in a higher dimensional bulk. Think of it like this. You live on the surface of a sheet of paper. The paper is 2-dimensional, but it sits in a 3-dimensional room. You can move left and right on the paper. You can move forward and backward, but you cannot move off the paper into the 3rd dimension. You are stuck on the surface. The 3rd dimension exists. The room is real. But you cannot access it. You can only move within your 2-dimensional sheet. Now add a dimension. Our universe is a 3-dimensional brane floating in a higher dimensional space. We can move in 3 directions within the brane. We cannot move into the bulk. The extra dimensions are right there, perpendicular to every direction we know, but we are confined to the brane. This is the brane world scenario, and it changes how we think about the universe. If we live on a brane, then the observable universe, the 93 billion light-year bubble, is not the full extent of reality. It is just the extent of our brane. Space continues beyond the brane, into the bulk, in directions we cannot perceive. And here is the strange part. There could be other branes, other 3-dimensional universes, floating in the same bulk, separated from us by a tiny distance in a higher dimension. Parallel universes in the most literal sense, not causally disconnected by distance or inflation. Physically close, maybe only a millimeter away, but in a direction we cannot point to because that direction is outside our brane. One of the most intriguing ideas to come out of brane world models is an explanation for why gravity is so weak. Gravity is by far the weakest of the 4 fundamental forces. The electromagnetic force, the force that holds atoms together and makes magnets stick to your fridge, is about 10 to the power of 36 times stronger than gravity. That is a stupidly large gap. Why is gravity so much weaker than everything else? Standard physics does not have a great answer. Brane world models offer one. Maybe gravity is not weak. Maybe it just looks weak because it is leaking into the extra dimensions. In brane world scenarios, all the forces we know, electromagnetism, the strong and weak nuclear forces, are confined to the brane. The particles that carry those forces, photons, gluons, W and Z bosons, cannot leave the brane. They are stuck on the surface, just like us. But gravity is different. Gravity, in general relativity, is not a force in the traditional sense. It is a curvature of space-time. And if space-time extends into the bulk, then gravity can spread into the extra dimensions. When you feel the pull of Earth's gravity, most of that gravitational field is trapped on our brane, but some of it leaks into the bulk, spreading out into higher dimensions we cannot access. That leakage dilutes gravity's strength within our brane. It is like shining a flashlight in a large room versus a small closet. The same amount of light spreads over a much larger area in the large room, so it looks dimmer. Gravity spreads into extra dimensions, so it looks weaker on our brain. This idea makes a testable prediction. If gravity is leaking into extra dimensions, then at very short distances, smaller than the size of the extra dimensions, gravity should behave differently. It should get stronger faster than Newton's law predicts. Experiments have been designed to test this. Physicists have measured the gravitational force between objects separated by distances as small as a fraction of a millimeter, looking for deviations from the expected behavior. So far, they have not found anything. Gravity still follows Newton's inverse square law down to the smallest scales we can measure. That does not rule out extra dimensions. It just means if they exist, they are smaller than the experiments can probe. The search continues. Brown worlds also offer a possible explanation for the Big Bang. If our universe is a brain floating in a higher dimensional bulk, then maybe the Big Bang was not the beginning of everything. Maybe it was a collision between two brains. Picture two sheets of paper floating in space. They drift toward each other, touch, and the collision releases an enormous amount of energy. That energy floods both brains, reheating them, creating particles, initiating expansion. From our perspective, trapped on one of the brains, the collision looks like the Big Bang. A sudden eruption of energy and matter, the beginning of time. But from the perspective of the bulk, it is just two objects colliding. Time did not begin. The brains existed before the collision. They will exist after. The Big Bang is local, not universal. It is an event that happened to our brain, not the origin of all reality. This model is called the ekpyrotic universe, and it has some appealing features. It avoids the singularity problem, the moment at the beginning of the Big Bang where the equations break down and density becomes infinite. In the ekpyrotic model, there is no singularity. The brains collide, energy is released, but the density stays finite. The universe heats up, but it does not compress to a point. The model also predicts specific patterns in the cosmic microwave background that could, in principle, distinguish it from standard inflation. Those patterns have not been detected yet, but the search is ongoing. If future observations find a signature that matches the ekpyrotic prediction and rules out inflation, it would be strong evidence that we live on a brain and that the Big Bang was a collision. Now take the brown world idea and push it further. If our universe is a brain and other brains exist in the bulk, what happens if those brains get close to each other? Not colliding, just passing nearby. The gravitational fields of both brains would overlap. Matter on one brain would feel a faint pull from matter on the other brain, even though the two brains are not in contact. From our perspective, it would look like gravity behaving strangely, objects accelerating without a visible source of mass. Dark matter. Some physicists have proposed that dark matter, the invisible substance that makes up about 27% of the universe's mass, might not be matter on our brain at all. It might be ordinary matter on a nearby brain. We cannot see it because light is confined to our brain. Photons cannot jump from one brain to another. But gravity leaks into the bulk, so we feel the gravitational pull of matter on the other brain, even though we cannot observe it directly. From our point of view, there is mass that we cannot see. We call it dark matter. But it is not dark. It is just on the other side of a dimensional boundary we cannot cross. This idea is speculative. Most cosmologists think dark matter is more likely to be a new type of particle that interacts very weakly with normal matter, something we have not discovered yet. But the brown world explanation is on the table. It fits the data. It makes predictions. And it is one more example of how higher dimensions change the game. They offer new explanations for old mysteries. They expand the set of possibilities. And they force us to rethink what we mean when we say the universe. If extra dimensions are real, they are not somewhere else. They are here. Every point in space has those dimensions folded into it. You are moving through 10 or 11 dimensions right now. You just do not notice because most of them are curled up too small to detect. Particles moving through your body, photons hitting your eyes, the electrons flowing through the circuits in your devices, all of them are propagating through a 10 or 11-dimensional space. The strings that make up those particles, if strings are real, are vibrating in patterns that involve all 10 or 11 dimensions. The physics we see, the forces, the masses, the charges, all of it is determined by how the strings move through the full geometry of space. We see 3 dimensions because those are the only ones large enough to navigate. The rest are hidden in the fine structure, too small to explore, but still there, still shaping everything. The challenge is that none of this is directly observable. You cannot build a microscope powerful enough to see a Calabi-Yau manifold. You cannot point a telescope at the bulk. The extra dimensions, if they exist, are beyond the reach of current technology and maybe beyond the reach of any technology. The scales involved are so far below what we can probe that indirect evidence is the best we can hope for. That evidence would come from patterns in particle collisions, anomalies in gravitational measurements, signatures in the cosmic microwave background, small deviations from what the standard model predicts, hints that the math needs more dimensions to make sense. So far, those hints have not materialized. The Large Hadron Collider, the most powerful particle accelerator ever built, has smashed protons together at energies high enough to probe scales far smaller than an atom. It discovered the Higgs boson, confirming the last missing piece of the standard model. But it has not found evidence of extra dimensions. It has not found supersymmetry, a related prediction of string theory. It has not found anything beyond the standard model. That does not mean string theory is wrong. It means either the extra dimensions are smaller than the LHC can probe, or the energy required to see their effects is higher than we can reach. The theory survives, but it does so without direct confirmation. Physicists are divided on how to feel about this. Some see string theory and M theory as the most promising paths forward, frameworks that could eventually unify all of physics if we just keep working on them. Others see them as beautiful ideas that have not delivered on their promises. Decades of work, brilliant minds, elegant mathematics, and still no experimental confirmation, no testable prediction that turned out to be right. No discovery that could only be explained by strings or brains or extra dimensions. The theories are consistent, but consistency is not the same as truth. There is a deeper question here, one that goes beyond string theory or M theory. If extra dimensions exist, what does that mean for the idea of beyond? The observable universe is 93 billion light-years wide. We have talked about what lies beyond that boundary. More space, maybe infinite, other bubble universes, quantum branches. But if reality has more dimensions than we perceive, then beyond is not just a question of distance, it is a question of direction. There could be entire universes sitting right next to ours in a higher dimension, separated by less than the width of an atom in a direction we cannot point to. We could be surrounded by other realities, other brains, other structures, and we would never know because we are confined to 3 dimensions. Our beyond is not just far away, it is perpendicular to everything we can see. That is a strange place to end up. The universe is not a box with walls at the edge. It is not a bubble floating in an infinite void. It might be a three-dimensional slice of a much larger structure, and that structure has geometry we cannot visualize and dimensions we cannot access. The fabric of reality is more complex than three directions and time. It might have 10 dimensions, it might have 11, it might have more, depending on which version of the theory turns out to be correct. And those dimensions are not empty mathematical abstractions. They are real geometric spaces, folded and hidden, but still part of the physical universe. This is not the kind of answer people expect when they ask what lies beyond the edge of the universe. They expect more galaxies, or empty space, or maybe a wall. They do not expect the answer to be extra dimensions curled up inside every point in space. But that is where the best physics we have is pointing. Not toward an edge in the distance, toward a hidden architecture woven into the structure of space itself, a geometry that includes us, but extends beyond us in directions we cannot follow. If the multiverse hypothesis asks whether there are other universes, the higher dimensional picture asks whether the concept of universe is even the right word. Maybe what we call the universe is just one cross-section of a higher dimensional object, one brain in a bulk filled with brains, one slice through a geometry too complex to visualize. The full structure would include all the brains, all the extra dimensions, all the ways space can curve and fold and compactify. That structure is reality. The universe is just the part of it we can see. And if we cannot see the full structure, if we are trapped in three dimensions, staring at shadows of higher dimensional shapes, then the next question is not what lies beyond. The next question is what gives rise to all of it. What is the thing underneath? The substrate that allows dimensions to exist in the first place. What is space, really? What is time? Why does anything exist at all? Those are not questions you answer by looking farther out into space. They are questions you answer by looking deeper into the foundations, into the quantum realm, where space and time themselves stop being smooth and continuous and start looking like something much stranger. That is where the origin lives, not at the edge of the universe, at the bottom of the structure, and that is where the story goes next. Reality does not start with atoms. It does not start with particles. It starts with something stranger, something that existed before the first particle ever appeared, before the first atom ever formed, before space and time took the shape we recognize. It starts with fields, invisible, intangible, mathematical structures that fill every cubic centimeter of space and have filled every cubic centimeter since the beginning. These fields are not made of anything. They are the things that everything else is made from. And the story of where the universe came from, how it began, why there is something rather than nothing, that story does not start with a bang. It starts in the quantum realm, where the rules are different, where nothing is ever truly empty, and where the line between existence and non-existence blurs into something nobody fully understands. This is not comfortable territory. The quantum realm does not behave the way your brain expects reality to behave. Particles appear and disappear. Energy emerges from what looks like empty space. Cause and effect stop working in the sequence you are used to. And yet this strange, unsettling layer of reality is the foundation. Everything you can see, touch, measure, all of it is built on quantum fields, doing things that should not make sense but somehow do. If you want to understand what lies at the edge of the universe, or beyond it, or beneath it, you have to go down to this level first. Because the quantum realm is not just where particles live. It might be where universes come from. Let's start with what a field is, because the word gets thrown around in physics and most people nod along without really knowing what it means. A field is a quantity that has a value at every point in space. Temperature is a field. The air in a room has a temperature at every location. Move from one corner to another and the temperature might change, but there is always a value. You can map it. The electromagnetic field is another example. At every point in space, there is a value for the electric field and a value for the magnetic field. Those values change depending on where you are and what charges or currents are nearby. But the field itself is everywhere. It fills all of space, always has, always will. In classical physics, fields were useful mathematical tools, a way to describe forces without having to track every individual particle. But in quantum physics, fields are fundamental. They are not descriptions of reality, they are reality. Every particle you have ever heard of, electrons, quarks, photons, neutrinos, all of them are excitations of an underlying quantum field. An electron is not a tiny ball of matter zipping through space. It is a ripple in the electron field, a localized disturbance in a field that exists everywhere. When you see an electron, you are seeing the field in an excited state. When the electron disappears, the field relaxes back to its ground state. The electron was never a thing. It was an event, a pattern of energy moving through a structure that never goes away. There is a quantum field for every type of particle. The electron field, the quark field, the photon field. Each field fills all of space, and each one can be excited in different ways to produce the particles we observe. The universe is not made of particles sitting in empty space. It is made of overlapping fields, each one vibrating, each one capable of creating particles when it has enough energy. The particles are temporary, the fields are permanent. That shift in perspective, from particles as objects to particles as excitations, is one of the most important conceptual changes in the history of physics, and it is the foundation for everything that follows. Now here is where it gets strange. The ground state of a quantum field, the state where there are no particles, is not actually empty. It is not zero. Quantum mechanics does not allow a field to sit perfectly still at exactly zero energy. There is always uncertainty, always fluctuation. Even in the vacuum, even in a region of space where there are no particles, the fields are active. They are fluctuating, popping in and out of higher energy states for brief moments, creating what physicists call virtual particles. These are not particles in the sense that you can catch them or measure them directly. They exist for such a short time that they do not violate the laws of physics, thanks to something called the Heisenberg uncertainty principle. Energy can be borrowed from the vacuum as long as it is paid back quickly enough. And that borrowing and repaying happens constantly, everywhere, at every point in space. This is vacuum energy, the energy of empty space. It is not a lot per cubic meter, but it is not zero. And when you add it up over the entire universe, it becomes significant. Some physicists think vacuum energy is what we call dark energy, the mysterious force driving the accelerated expansion of the universe. Others are not so sure. But the point is this: empty space is not empty. The vacuum is seething with activity, quantum fluctuations, virtual particles appearing and disappearing, fields buzzing at their lowest energy state, which is still not nothing. The universe, at its most fundamental level, is never silent. It hums. That hum is real. It has measurable effects. One of the most famous is called the Casimir effect, discovered in 1948 by a Dutch physicist named Hendrik Casimir. He predicted that if you place two uncharged metal plates very close together in a vacuum, they will feel a force pulling them toward each other, not because of gravity, not because of electromagnetism, because of quantum fluctuations. The space between the plates is so narrow that only certain wavelengths of virtual particles can fit. Outside the plates, all wavelengths are allowed. The imbalance in vacuum energy between the inside and the outside creates a pressure. The plates get pushed together. Experiments confirmed this. The force is tiny, but it is real. The vacuum is doing work. Empty space has structure. So the quantum vacuum is not a void. It is a dynamic, fluctuating substrate. And once you accept that, a very strange question becomes unavoidable. If quantum fields can fluctuate, if energy can appear from nothing for a brief moment, if the vacuum is not truly empty, then could the universe itself be a quantum fluctuation? Could space, time, matter, all of it, be something that popped into existence the way a virtual particle pops into existence? Not created by something outside the system, not designed or intended, just allowed by the rules of quantum mechanics, a fluctuation that got lucky and stuck around. This is not a fringe idea. It is a serious line of inquiry in a field called quantum cosmology. The idea goes like this. Before the Big Bang, assuming before even makes sense, the universe was in a quantum state, not a classical state with definite properties, a superposition, a probabilistic fog where space and time were not yet well defined. The geometry itself was fluctuating. In most of those fluctuations, nothing interesting happens. The fluctuation collapses back into the vacuum. But in rare cases, a fluctuation is large enough and energetic enough that it inflates, expands, and becomes a universe. Our universe might be one of those rare events, a quantum blip that did not collapse, a fluctuation that grew into everything we see. The math for this is complicated and speculative, but it is grounded in real physics. Quantum mechanics allows for tunneling, a process where a system can jump from one state to another, even if it does not have enough energy to cross the barrier in between. Particles do this all the time. An electron on one side of a barrier can appear on the other side without passing through the middle. The probability is low, but it is not zero. Apply that idea to the universe itself, and you get something called quantum tunneling from nothing. A universe that tunnels into existence from a state where there was no space, no time, no energy. Not nothing in the sense of empty space. Nothing in the sense that the concepts of space and energy do not apply yet. A pre-geometric state, a quantum foam. Quantum foam is a term coined by physicist John Wheeler in the 1950s. It describes what space might look like at the smallest possible scales, the Planck scale, about 10 to the power of negative 35 meters. At that scale, quantum fluctuations are so violent that space and time lose their smooth, continuous structure. They become grainy, foamy, chaotic. Distances stop being well-defined. Time stops being a single forward-flowing dimension. The geometry itself fluctuates. Tiny wormholes open and close. Virtual black holes appear and evaporate. Space at the Planck scale is not a calm backdrop. It is a roiling sea of quantum activity. And in that sea, anything allowed by the laws of quantum mechanics can happen, including the birth of a universe. Some models describe the pre-Big Bang state as a cosmic egg, not a physical object, a quantum state, a region of quantum foam where the conditions were right for a large fluctuation to occur. The fluctuation created a bubble of space, and that bubble inflated. Inflation, the exponential expansion we talked about earlier, took over. The bubble grew from something smaller than an atom to something larger than the observable universe in a fraction of a second. When inflation ended, the energy driving it decayed into particles, radiation, matter. The universe heated up. Space continued expanding, but now at a slower rate. That transition from inflation to normal expansion is what we call the Big Bang. It was not the beginning of everything. It was the moment the bubble transitioned from a quantum state to a classical state, the moment the universe became something we could describe with normal physics. This picture avoids the singularity problem. In the standard Big Bang model, if you run the clock backward, the universe gets smaller and denser until it reaches a point of infinite density and infinite temperature, a singularity. The equations break down. Physics stops making sense. General relativity, which describes the Big Bang, cannot handle singularities. It predicts them, and then it fails. Quantum cosmology tries to get around this by saying the universe never passed through a singularity. At the earliest moments, quantum mechanics was in control, and quantum mechanics does not allow infinite density. The universe was in a quantum superposition, a fuzzy probabilistic state, and it transitioned smoothly from that state into the classical expanding universe we observe. No singularity, no breakdown, just a quantum to classical transition. One of the most famous models along these lines is called the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s. Their idea is that the universe has no boundary in time. If you go back to the very beginning and ask what came before the Big Bang, the answer is nothing came before because there was no before. Time itself emerged from the quantum state. Imagine the surface of the Earth. You can travel south, and you will eventually reach the South Pole. If you ask what is south of the South Pole, the question does not make sense. There is no south of the South Pole. South is a direction defined on the surface of the Earth, and the South Pole is the point where that direction stops being meaningful. The Hartle-Hawking model says the Big Bang is like the South Pole. It is the boundary of time, but there is no edge, no moment before. Time curves back on itself in a way that makes the question what came before invalid. The model uses something called imaginary time, a mathematical tool where time is treated as a complex number. In imaginary time, the distinction between space and time blurs. The geometry of the early universe becomes smooth and finite, like the surface of a sphere. No singularity. No beginning in the traditional sense, just a closed surface where time is one of the dimensions. It is an elegant idea, and the math works, but it is also deeply strange. Imaginary time is not something we experience. It is a calculational device. Whether it represents something real or just a useful trick is an open question. Hawking himself was cautious about making strong claims. He described the no-boundary proposal as a model, not a definitive answer, a way to think about the problem, not the final word. Another approach comes from loop quantum gravity, a competitor to string theory. Loop quantum gravity tries to quantize space itself, breaking it down into discrete chunks called quanta of geometry. At the Planck scale, space is not continuous. It is made of tiny loops, each one representing a minimal unit of area or volume. Time is also quantized, chopped into discrete moments. In this framework, the Big Bang singularity is replaced by a big bounce. The universe did not start from nothing. It contracted from a previous phase, reached a minimum size determined by quantum geometry, and then bounced back into expansion. Our universe is the outgoing phase of a bounce. Before the bounce, there was another universe, contracting. Before that, maybe another bounce. The model allows for a cyclical cosmology, an eternal sequence of expansion and contraction, with no true beginning and no true end. Loop quantum gravity makes specific predictions about the early universe that could, in principle, be tested. The bounce would leave an imprint on the cosmic microwave background, a signature different from what standard inflation predicts. Observations have not found that signature yet, but the search continues. If the bounce model is correct, the Big Bang was not the origin of everything. It was a transition, a moment when one phase of the universe ended and another began. The full story extends backward in time, through the bounce, into a previous contracting phase. And if that phase also came from a bounce, the timeline stretches infinitely into the past. These models, Hartle-Hawking, loop quantum gravity, eternal inflation, all of them are attempts to answer the same question: where did the universe come from? And all of them avoid the need for a first cause, a moment of creation, a prime mover. They describe the universe as self-contained. Either time loops back on itself, or the universe bounces, or it emerges from a quantum fluctuation that was always allowed by the laws of physics. The laws themselves are not explained. Nobody knows why quantum mechanics works the way it does, or why the universe obeys these particular equations. But given the laws, the origin of the universe becomes a natural consequence, not a miracle, not a violation, just something that was bound to happen eventually. There is a philosophical weight to this. If the universe can emerge from a quantum fluctuation, if it can tunnel into existence from nothing, then the question, why is there something rather than nothing, loses some of its force. The answer is because nothing is unstable. Because quantum mechanics does not allow a system to sit perfectly still at zero. Because fluctuations happen, and given enough fluctuations, or an infinite amount of time, or a multiverse with infinite opportunities, something like our universe was inevitable. You do not need a creator, you do not need intention. You just need the laws of quantum mechanics and the passage of time. And if time itself emerged from the quantum state, you do not even need that. The universe is a self-starting process. Not everyone is comfortable with this. Some physicists argue that appealing to quantum mechanics to explain the origin of the universe is circular. Quantum mechanics is a set of rules. Where did the rules come from? If the universe is a quantum fluctuation, what is the thing doing the fluctuating? You cannot say the quantum fields were fluctuating because quantum fields are part of the universe. They exist in space. If there is no space yet, there are no fields. Some models try to get around this by invoking a pre-geometric state, a kind of proto-reality where the concepts of space, time, and fields do not yet apply. But describing that state requires mathematics we do not fully understand. The equations work in certain limits, but pushing them all the way back to the origin leads to ambiguities and uncertainties. The models are suggestive, they are plausible, but they are not definitive. There is also the question of testability. Can we ever observe the quantum state of the early universe? Can we measure the effects of a big bounce or a no-boundary condition? The cosmic microwave background is our best window into the early universe, and it has already given us an enormous amount of information. But the CMB only shows us the universe at 380,000 years old. Everything before that is hidden behind the opaque fog of the early plasma. Gravitational waves from the inflationary era, if they exist, might carry information about earlier moments. Experiments are being designed to detect them, but even if we find those waves, they will only take us back so far. The very first moments, the Planck scale era, might be permanently out of reach. The energies involved are so high and the scales so small that building an experiment to probe them directly is beyond anything we can currently imagine. So we are left with models. Educated guesses built on solid physics, but extended into regimes where the physics becomes uncertain. Quantum cosmology is not settled science. It is frontier science. The ideas are serious, the researchers are credible, but the conclusions are tentative. The universe might have emerged from a quantum fluctuation. It might have bounced from a previous contracting phase. It might have no boundary in time. Or the true answer might be something none of these models have captured yet. We are still figuring it out. But here is what we do know. The quantum realm is not optional. It is not a layer of reality you can ignore when thinking about the big picture. It is the foundation. Particles are excitations of fields. Fields fluctuate even in the vacuum. The vacuum has energy. That energy can do work. And at the smallest scales, at the Planck scale, space and time themselves become quantum objects, subject to the same uncertainty and fluctuation as everything else. The smooth, continuous, predictable universe we experience at human scales is an emergent phenomenon. Underneath, at the bottom, reality is grainy, probabilistic, strange, and it has been that way since the beginning. If the quantum realm can give rise to particles from vacuum fluctuations, if it can create forces and energy from what looks like nothing, then the leap to saying it can create a universe is not as large as it seems. It is the same process, just scaled up. A fluctuation large enough and energetic enough to become a bubble of space, a bubble that inflated, cooled, and filled with matter. The math allows it. The physics, as far as we understand it, does not forbid it. And in a realm where everything that is not forbidden is mandatory, given enough time or enough opportunities, a universe becomes inevitable. This is a very different picture from the one most people carry around. The idea that the universe started with a big bang, a sudden explosion from nothing, is a simplification. It is not wrong exactly, but it is incomplete. The Big Bang was not an explosion in space. It was an expansion of space, and it was not the beginning of everything. It was the transition from a quantum state to a classical state. Before the Big Bang, the universe was not nothing. It was something we do not have good words for, a quantum superposition, a fluctuation in a pre-geometric substrate, a bubble nucleating in a sea of possibilities. The Big Bang is the moment that bubble became large enough and stable enough to be described by the physics we know. And if our universe is one bubble, one fluctuation, then the process that created it is probably still happening. Somewhere, in some region of the quantum foam, another bubble is nucleating. Another universe is starting. The multiverse is not just a consequence of inflation. It is a consequence of quantum mechanics applied to cosmology. The vacuum is never truly stable. It is always fluctuating. And fluctuations, given the right conditions, can grow. We live in one of those fluctuations. A universe that started small, inflated, cooled, and became the 93 billion light-year sphere we can observe. But the process that made us is not unique. It is a feature of the quantum realm, and features do not happen just once. So the question of what lies beyond the edge of the universe is also a question of what lies beneath it. Beneath the particles, beneath the fields, beneath space and time themselves, there is a quantum substrate, a layer of reality where the rules are different, where uncertainty and fluctuation dominate, where the line between existence and non-existence is not a line at all. That substrate is not somewhere else. It is here. It is the foundation of everything, and it might be the origin of everything too. The quantum realm does not answer every question. It does not tell us why the laws of physics are what they are. It does not explain why there is something rather than nothing in an ultimate sense. But it does show us that nothing is not stable, that the vacuum is active, that space and time and matter can emerge from processes that are, at their core, quantum mechanical. The universe is not a static object placed into existence by an external force. It is a dynamic, evolving structure that began in a quantum state and has been unfolding ever since. And if that is true, then the story of the universe is not a story with a clear beginning and a clear end. It is a story embedded in a larger structure, a quantum foam, or a multiverse, or a higher dimensional space, where beginnings and endings are just transitions. Our universe is one chapter in a much longer book, one bubble in a much larger foam, one fluctuation in an ongoing process that might have no start and no finish. The quantum realm is not the answer to everything, but it is the place where the answers, if they exist, are going to come from. We are standing at the edge of the known. The observable universe is the farthest we can see with light. The quantum realm is the deepest we can probe with mathematics. And somewhere in between those two frontiers, in the interplay between the very large and the very small, is the truth about where we came from and what else is out there. We do not have the full picture yet. We might never have it, but we are closer than we have ever been. Closer to understanding the fabric of reality. Closer to seeing how the universe fits into something larger. And closer to accepting that the thing we call the universe might just be one instance of a process that happens over and over, in ways we are only beginning to imagine. That process is not happening somewhere far away. It is happening everywhere, all the time, in the quantum fluctuations that fill every point in space. The edge of the universe is not a place, it is a concept. And the concept is dissolving the more we learn. What lies beyond is not another place, it is another way of thinking, another framework, another layer of reality that we are only now starting to glimpse. And that glimpse, unsettling as it is the closest thing we have to an answer. We have spent 7 chapters walking the boundaries of everything we can measure, mapping the contours of the observable, and staring into regions we can never reach. We have followed the light back to the moment the universe became transparent. We have watched galaxies accelerate beyond the edge of observation. We have considered bubbles and brains, quantum foam and hidden dimensions, the possibility that our universe is one voice in an infinite choir we will never hear. And now we are here, at the end of the line, the place where science meets the limits of what science can do. Not because we lack better instruments or smarter theories, but because the universe itself has drawn a line in the geometry of space-time, and that line says no further. The observable universe is 93 billion light-years wide. That is not a guess. It is a measurement derived from the age of the cosmos, the speed of light, and the rate at which space has been expanding. The number is solid. The boundary it describes is real. And yet, that boundary is not an edge in any physical sense. It is a horizon, a limit to observation, not a limit to existence. Beyond that horizon, space continues. Galaxies keep forming. Stars keep dying. The universe keeps doing what it has always done, indifferent to whether anyone is watching. We just cannot see it. Not now, not ever. The light has not had time to reach us, and because of the accelerating expansion, much of it never will. We are sealed inside a bubble of information, surrounded by a cosmos that is permanently out of reach. That statement should bother you more than it probably does. We are not talking about distant galaxies that are hard to see or faint signals that require better technology. We are talking about a fundamental, absolute barrier, a wall built not of matter or energy, but of causality itself. The regions beyond the particle horizon are not just far away, they are unknowable. No signal from those regions can ever cross the gap. No photon, no gravitational wave, no particle, no information of any kind. The laws of physics do not just make observation difficult, they make it impossible. That is a different kind of limit. It is not a technical challenge to overcome. It is a feature of the structure of reality. And yet, for 7 chapters, we have been asking what lies beyond. We have built models, made predictions, explored possibilities. We have talked about infinite space and closed geometries, bubble universes and quantum branches, strings vibrating in 10 dimensions, and fields fluctuating in the vacuum. None of that came from observation. It came from extrapolation, from taking the rules we can measure and extending them into regions we cannot. That process is the backbone of theoretical physics. You observe what you can, figure out the rules, and then ask what those rules imply about the things you cannot observe. Sometimes it works. General relativity predicted black holes decades before we found them. Quantum mechanics predicted antimatter before anyone detected a positron. The history of physics is full of examples where theory led and observation followed. But it is also full of examples where theory ran ahead of itself, predicted things that turned out to be wrong, or worse, predicted things that could never be tested. The multiverse might be one of those cases, or it might not. We do not know yet. And that ambiguity is what makes this moment in cosmology so strange. The scientific evidence for what lies beyond the observable universe is indirect at best. We know space is expanding. We know the expansion is accelerating. We know the early universe went through a period of rapid inflation. We know quantum fields fill all of space and fluctuate even in the vacuum. We know the constants of physics are finely tuned in ways that seem unlikely unless there are many universes with different constants. All of that is solid, measured, confirmed by observation. The leap happens when we ask what those facts imply. If inflation happened here, did it happen elsewhere? If quantum fields fluctuate, can those fluctuations create universes? If the constants are tuned, is it because we live in one universe among many, or because something else is going on that we have not figured out yet? The evidence does not answer those questions directly. It points in certain directions. It makes some possibilities seem more plausible than others, but it does not prove anything beyond the horizon. And that is the enduring mystery. We have pushed observation as far as it can go. The cosmic microwave background is the oldest light we will ever detect. The particle horizon is as far as we will ever see. Future telescopes might sharpen the images, tighten the measurements, detect fainter signals, but they will not push the boundary back in any meaningful way. The horizon is set by the age of the universe and the speed of light. Those numbers are not going to change, which means the list of things we can observe is essentially complete. The catalogue might get more detailed, but the catalogue itself is closed. Everything outside that list is inference, extrapolation. Theory built on top of theory, anchored to observation at the base, but stretching into territory where observation cannot follow. That does not mean the theories are useless. It means they are a different kind of science. Theoretical physics has always operated in this space, asking questions that cannot be answered by experiment alone. Why do particles have the masses they do? Why does the universe have 3 dimensions? Why is there more matter than antimatter? Some of those questions eventually connect back to observation, others might not. The multiverse question might be one of the latter. If other universes exist, and we can never interact with them, never detect them, never measure their properties, then the multiverse is not a scientific hypothesis in the traditional sense. It is a consequence of a hypothesis, a side effect of taking inflation or quantum mechanics or string theory seriously. The hypothesis itself, inflation or quantum mechanics or string theory, is testable. The multiverse is what you get when you follow the math all the way through. And if the math works, if the testable parts of the theory keep matching observation, then the untestable parts gain credibility by association, not proof, credibility, a kind of provisional acceptance based on the assumption that the universe does not change its rules halfway through. Some physicists hate this. They argue that science without testability is not science, it is philosophy, or mathematics, or storytelling. And they have a point. The scientific method is built on observation, hypothesis, experiment and revision. If you remove experiment from that loop, what is left? The answer, according to the people who work on these problems, is consistency, internal logical coherence, predictive power in the regions you can test, and a kind of explanatory elegance where a single framework accounts for multiple observations without adding unnecessary complications. Inflation explains the uniformity of the cosmic microwave background, the flatness of space, and the origin of density fluctuations. It does all that with one mechanism, and as a side effect, it predicts eternal inflation and bubble universes. You do not get to keep the parts you like and throw out the parts you do not. The theory is a package. Either it works or it does not. Theoretical physics is pushing the boundaries of understanding in ways that observation alone never could. Observation tells you what is. Theory tells you what could be and why. The two are supposed to work together. Observation constraining theory, theory guiding observation. But at the edges, at the frontiers, the balance shifts. Theory runs ahead. It has to. The questions we are asking now are too big, too remote, too fundamental to wait for observation to catch up. What is the structure of space at the Planck scale? What happened in the first moments after the Big Bang? Are there other universes? Why do the constants have the values they do? Why is there something rather than nothing? Observation cannot answer those questions directly because the scales are too small, the energies too high, the distances too far. Theory is the only tool we have, and theory at this level is more like exploration than experimentation. You build a model, work out its implications, see if it matches what you can observe, and if it does, you take it seriously. If it does not, you revise or discard it. The process is slower, less definitive, and more speculative than traditional science, but it is not arbitrary. The models are grounded in math that works. The predictions, where they can be tested, often turn out to be right. And the frameworks that survive are the ones that explain the most with the least. String theory is a perfect example of this. It unifies gravity and quantum mechanics, something no other theory has managed to do. It predicts particles we have not found yet, but it also predicts particles we have. It requires extra dimensions, which we have not detected, but it explains why gravity is so weak, which is something we have observed. The theory works in the sense that the math is consistent, and the predictions it makes in testable regimes match reality. The untestable parts, the extra dimensions, the landscape of possible universes, those are consequences, not assumptions. You do not add them to the theory, they fall out of it. And if the testable parts keep working, the untestable parts gain weight, not certainty, weight. A kind of intellectual gravity that pulls the community toward taking them seriously, even in the absence of direct proof. Quantum cosmology is the same. The idea that the universe emerged from a quantum fluctuation is not something you can test by rerunning the Big Bang in a lab. But it is a natural consequence of applying quantum mechanics to the early universe. And quantum mechanics itself is the most tested theory in the history of physics. Every prediction it has made at the scales we can probe has been confirmed. So when quantum cosmology says the vacuum is not empty, that space and time can fluctuate, that a universe can nucleate from a quantum state, those are not wild guesses. They are extrapolations of rules that work everywhere else. The extrapolation might be wrong. The Planck scale might be governed by physics we have not discovered yet, but the default assumption, the one that has worked for 300 years, is that the rules do not change. If quantum mechanics applies here, it applies there. If fields fluctuate in the lab, they fluctuate in the early universe. And if fluctuations can create particles, they can create universes. The reasoning is sound, even if the conclusion is strange. But soundness is not the same as truth. And that gap, that space between what the theory says and what we can confirm, is where the philosophical questions live. If other universes exist, and we can never observe them, does it matter? If the constants of physics are different in other bubbles, and we can never visit those bubbles, do those constants count as real? If the multiverse explains fine-tuning by saying every possibility happens somewhere, is that an explanation or an evasion? These are not scientific questions in the sense that experiments can resolve them. They are questions about what counts as knowledge, what counts as reality, and what role observation plays in defining both. One answer, the one most scientists default to, is that reality is what is, not what we can see, not what we can measure, what is. If other universes exist beyond our horizon, they are real whether we observe them or not. The observable universe is a subset of the universe, not the full set. Our inability to see beyond the horizon is a limitation of our position, not a statement about what exists. This is called realism, the view that the world exists independently of our observations. It is the assumption that underlies all of science. You do not stop believing in atoms when you close your eyes. You do not stop believing in distant galaxies when you turn off the telescope. The things you cannot see are still there. The multiverse, if it exists, is still there, beyond the horizon, beyond the reach of light. Real, physical, governed by the same kinds of laws that govern our universe, even if those laws produce different outcomes. The other answer, the more cautious one, is that reality is what we can verify. If a claim cannot be tested, it does not belong in science. It might be true. It might be interesting, but it is not scientific knowledge. This is called empiricism, the view that knowledge comes from observation and anything beyond observation is speculation. Empiricism has a strong track record. It is the reason science works. Theories that make testable predictions survive, theories that do not get replaced. The multiverse, in this view, is not a theory. It is a hypothesis that might turn out to be a consequence of a theory. And until the consequence produces a testable prediction, it stays in the category of interesting ideas rather than established facts. That does not mean it is wrong. It just means it is not yet part of the scientific canon. Both views are defensible. Both have shaped the history of physics. And the tension between them is part of what makes this moment so interesting. We are at a point where the best theories we have predict things we might never be able to observe. That has happened before, but not at this scale. Black holes were predicted in 1916 and confirmed in the 1970s. Gravitational waves were predicted in 1916 and confirmed in 2015. The Higgs boson was predicted in 1964 and confirmed in 2012. Theory led, observation followed, and the time gap closed. But the multiverse might be different. The time gap might never close. The regions beyond the horizon might stay beyond the horizon forever. And if that is the case, the multiverse will remain a theoretical construct, supported by the success of the theories that predict it, but never directly confirmed by observation. Some physicists are fine with that, others are not. The debate is ongoing. What is not up for debate is the fact that we live in a universe that is larger and stranger than anything humans imagined even a century ago. The observable universe is 93 billion light-years wide, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. The cosmos is expanding, accelerating, driven by a form of energy we do not understand. The matter we can see makes up less than 5% of the total. The rest is dark matter and dark energy, invisible components that dominate the universe but remain undetected in the lab. Space itself might have extra dimensions, curled up at scales too small to probe. Time might have emerged from a quantum state where the concept of before did not apply. The universe might be one bubble in an infinite foam, one branch in an infinite tree of possibilities. All of that is on the table, not as certainty, as serious, mathematically grounded, observationally motivated possibility. And the fact that we have reached this point, that we can even ask these questions, is extraordinary. A century ago, we did not know galaxies existed. We thought the Milky Way was the entire universe. We had no idea space was expanding, no idea the universe had an age. No concept of the Big Bang, or inflation, or dark energy, or quantum fields. The questions we are asking now would have been incomprehensible to the scientists of 1920, and the answers we have found, partial and incomplete as they are, would have seemed like science fiction. Yet here we are, mapping the cosmic microwave background with precision down to millionths of a degree, detecting gravitational waves from colliding black holes a billion light-years away, imaging galaxies as they existed 300 million years after the Big Bang, building theories that unify forces, predict particles, and describe the origin of space and time. The progress is real. The knowledge is accumulating, and the frontier keeps moving. But the frontier has a limit. That is the uncomfortable truth. There is a boundary to what we can observe, and that boundary is not going to move much farther. We have reached the edge of the observable. Everything beyond that edge is inference, and inference, no matter how well grounded, is not the same as observation. We will never see the other side of a bubble universe. We will never measure the constants of physics in a parallel branch. We will never detect the geometry of the extra dimensions if they are smaller than the Planck length. The tools we have, telescopes, particle accelerators, gravitational wave detectors, all of them are bounded by the same fundamental limits: the speed of light, the age of the universe, the energy scales we can reach. Those limits are not technical, they are physical, built into the structure of reality, and they are not going away. So what does that mean for us? For humanity, sitting on a small planet orbiting an average star in an unremarkable galaxy, staring out at a cosmos that stretches beyond comprehension. What does it mean to know that most of reality is out of reach? That the observable universe is a tiny fraction of the whole? That the questions we most want answered might be unanswerable? One response is humility. We are not at the center of anything. Not the center of the solar system, not the center of the galaxy, not the center of the universe. There is no center. We are one planet in a vast cosmos, and the cosmos does not care whether we understand it. The universe is not here for us. It is here because the laws of physics allow it to be here, and we happen to exist in a corner of it where the conditions are right for life. That is not a depressing thought. It is a liberating one. The universe does not owe us answers. The fact that we have found any answers at all is a triumph of curiosity, intelligence, and persistence. Every measurement we make, every theory we build, every observation that matches a prediction is a victory against the default state of ignorance. We started knowing nothing. We have learned an astonishing amount. And the fact that there are limits to what we can learn does not diminish what we have already accomplished. Another response is awe. The universe is bigger, older, and stranger than we ever imagined. And we figured that out, not by guessing, by observing, measuring, calculating, by building instruments sensitive enough to detect the faint glow of the Big Bang, by solving equations that describe the curvature of space-time, by running simulations that model the formation of galaxies, by thinking carefully about what the data implies and following the logic wherever it leads. The story we have uncovered is not simple. It is not comforting. It is not built to make us feel special, but it is beautiful. The cosmos governed by laws we can write down, filled with structures we can describe, evolving in ways we can predict. The fact that we can do any of that is remarkable. The fact that we can do it well enough to map the observable universe and speculate coherently about what lies beyond is almost miraculous. A third response is acceptance. There are things we will never know. The multiverse might be real. Extra dimensions might exist. The universe might have no beginning in time. Or it might have begun in a quantum fluctuation so far removed from anything we can measure that the details are lost forever. We might be living in a simulation. We might be one branch of a quantum superposition. We might be alone in the cosmos, or we might be surrounded by life we will never detect because the distances are too large and the signals too faint. Some of those questions might eventually be answered. Others might not, and that is fine. The universe does not owe us completeness. The pursuit of knowledge is valuable even when the knowledge is partial. Understanding that the observable universe is 93 billion light-years wide is progress. Understanding that it is expanding and why is progress. Understanding that the laws of physics produce galaxies and stars and planets is progress. The fact that we do not understand everything does not erase what we do understand. And the pursuit continues. New telescopes are being built, new detectors are coming online, new theories are being developed. The James Webb Space Telescope is already pushing the boundaries of what we thought was possible, finding galaxies that should not exist and forcing cosmologists to revise their models. Future missions will probe the cosmic microwave background with even greater precision, searching for the faint signatures of gravitational waves from the inflationary era. Particle accelerators are being designed to reach higher energies, probing deeper into the structure of matter. Gravitational wave observatories are being upgraded, preparing to detect signals from the early universe. The work is not stopping. The questions are not going away, and the possibility, however remote, that we might find a way to test the untestable, to observe the unobservable, to push past the limits we think are absolute, that possibility keeps the field alive, because history has a way of surprising us. Things we thought were impossible turn out to be hard. Things we thought were unknowable turn out to be measurable. Black holes were theoretical curiosities until we found them. Gravitational waves were mathematical predictions until we detected them. Exoplanets were science fiction until we started cataloging them by the thousands. The edge of the possible keeps moving, slowly, unpredictably, but it moves. And the universe, for all its size and strangeness, has been remarkably willing to give up its secrets to anyone patient and clever enough to ask the right questions. So the unknowable horizon is not a wall, it is a challenge. A reminder that the universe is larger than our ability to perceive it, but not larger than our ability to think about it. We can build models, we can test the parts we can reach. We can follow the implications and see where they lead. And even if we never confirm the multiverse, even if we never detect extra dimensions, even if the origin of the universe stays forever out of reach, the attempt is worth it, because the attempt is what defines us, not the answers, the pursuit. The refusal to accept ignorance as a permanent condition. The insistence that we can understand, even when understanding is hard, even when the questions are too big, even when the universe seems designed to keep its secrets. We live in a universe that may be infinitely larger and stranger than we can ever fully grasp. That is not a reason to stop looking. It is a reason to keep going, to build better instruments, to ask harder questions, to take the knowledge we have and push it as far as it will go. The observable universe is 93 billion light-years wide. What lies beyond is unknown. But the fact that we can ask the question, that we can map the boundary, that we can look at the data and say with confidence that there is more out there, more than we will ever see, that is enough. That is the human project. Not to know everything, to know as much as we can, and to keep reaching for the rest. We started with a number that should not make sense. 93 billion light-years wide, a universe older than the distance light should have been able to travel, an edge that is not an edge, a horizon that marks not where space ends, but where observation fails. And from there, we followed the threads outward, downward, inward, into regions that blur the line between science and something else, something stranger. The universe is expanding, and the expansion is accelerating, driven by an energy we cannot see and do not understand. Space itself is growing, pulling galaxies beyond the reach of light, erasing the evidence of its own history one photon at a time. The earliest galaxies formed faster than they should have. The constants of physics are tuned in ways that seem deliberate, but probably are not. The vacuum is not empty. Dimensions we cannot perceive might be folded into every point in space, and the thing we call the universe might be one bubble in an infinite foam, one branch in an endless tree, one fluctuation in a quantum substrate that has been churning since before time had meaning. None of that is comfortable. None of it feels designed for human comprehension. But all of it, every strange piece, follows from taking the rules we can measure and asking what those rules imply about the things we cannot. The math works, the observations fit, and the conclusion, unsettling as it is, keeps pointing the same direction. Reality is larger than we thought, stranger than we expected, and most of it is out of reach. That is not a failure, that is the condition. We live inside an observable bubble, surrounded by a cosmos we will never fully map, and yet we mapped it anyway, as far as observation allows, as far as theory can stretch. We know what lies at the edge of sight, and we know, with surprising confidence, what probably lies beyond. You are sitting on a planet that is 67,000 miles per hour around a star. That star is orbiting the center of a galaxy at 500,000 miles per hour. That galaxy is falling toward a cluster at over 1,000,000 miles per hour. And all of it, every galaxy, every cluster, every structure in the cosmic web, is being pulled apart by the expansion of space faster than anything can hold it together. You are moving, the ground beneath you is moving, and the motion never stops. And still, against all that chaos, we built instruments sensitive enough to detect light that has been traveling for more than 13 billion years. We measured fluctuations in the cosmic microwave background that differ by millionths of a degree. We found galaxies at the edge of time. We detected gravitational waves from colliding black holes 1 billion light-years away.